good enough. Now this representation is good enough if you want to convey the structure of a graph to someone. I could give you these two variables and then without showing you this image, and you could use this information to draw the graph on a piece of paper. So this representation is complete. It provides all the information about the graph, but it may not be efficient. For example, if you want to find out which nodes the node 1 is connected to, we would have to iterate over the entire list of edges. We would have to go through this one and then check if either of these is 1 and check if either of these is 1 and so on. So that makes it very tricky to access any information efficiently. Rather, it'll be much nicer to just look at a list of nodes that one is connected to in some way and go from there. Now, if you want to find the shortest path, we would first have to find all the nodes that one is connected to. And then for each of those, we would have to find their neighbors. And then for each of those, we would have to find their neighbors and so on. So it would get pretty tedious to go through the list so many times. So that's why, and by the way, by a neighbor, we mean two nodes that are connected by an edge. So 0 and 1 are neighbors, but 0 and 2 are not neighbors. Okay, so that's a very simple nomenclature that we can use. And what we can say is if we track the path, we say 0, 1, 2, and if there is an edge between both of them, we say that 0, 1, 2 is a path. So 0, 1, 2 in this case is a path, but 3, 0, 1 is not a path because there is no path, but there's no edge between 3 and 0. Okay. And we'll see what we mean by paths and neighbors and so on in some time. But to work with graphs more efficiently, we will represent them using what's called an adjacency list. Now, the name, it explains what it contains. So the adjacency list contains a list for each node, and it contains a list of all the nodes that are adjacent to that node. Now again, adjacency is the same as adjacent is same as neighbor. So if for each node, so for example, for the node 0, we maintain a list, and that list contains the numbers 1 and 4, indicating that 0 is adjacent to, or 0 is a neighbor of, or 0 is connected via a direct edge to 1 and 4. So that's why you have 1 and 4 here. And then 1 is connected to 0, 2, 3, and 4. You can see that 1 is connected to 0, 2, 3, and 4. Similarly, 2 is connected to 1 and 3, 3 is connected to 1, 2, 4, and 4 is connected to 0, 1, 3. Now this is more convenient for sure. One, because since this is a list, if you want to find, let's say, which nodes 2 is connected to, we can directly access the index 2 within the list. And this is why we number the vertices or number the nodes from 0 to n-1 so that we can access them directly in an adjacency list, right? So we directly access the numbers stored next to 2. And so we have 1 and 3 here. So that's what makes it convenient. And one important thing to notice here is that each edge occurs twice. So the edge 0, 1 shows up in the list for 0. So you can see here in the list for 0, we have 1. And similarly, in the list for 1, we have 0. So each edge shows up in two adjacency lists of each of the nodes that it connects. Okay. So now the obvious next question might be to create a class to represent a graph as an adjacency list in Python. Okay. This is again a question that you might get asked, or this might be part of another question that you may get asked where you're asked to perform a breadth first search or depth first search or find the shortest path. The first step you will have to do is define a class for a graph to maintain the information about the graph as the adjacency list. Okay, so here we're creating a class graph, and the first thing we'll need inside the graph is a constructor function. So we need to put something inside the constructor function, and we know that the first argument to any graph, any class method in Python is self, which represents the object that will get created ultimately when we create an object of the class. But apart from this, what information do you need to create a graph? Now it's pretty straightforward. We can simply work with this information because these two variables together specify the graph completely. So let's simply accept num nodes and a list of edges as the information. The first thing we can do is simply store num nodes in self.num nodes so that once we create a graph, we can access the number of nodes very easily. Then we need to create the adjacency list. So we need to create the adjacency list. We'll call it self.data. And initially we will create a list containing empty lists and then we will fill out the empty list step by step. So what we need is something like this. In this case, because there are five nodes, so this is what we need to create, the 5 empty lists. Now in general, the way to create repeated elements is this. You can say, if you want to create a repeated element like this, 0 times, you type 0 times 10, and that gives you this list, 0, 0, or containing all zeros. On the other hand, if you create empty list times 10, and let's call this L1, and let's see what L1 is. It looks like you've gotten an empty list, you've gotten a list containing 10 empty lists, but let's just go into the first element. So the first element is this first empty list, and inside the first element, let us add the value 1. Okay, and then let's look at the list L1 once again, and you see what happens. This 1 gets inserted into all of these lists. Now what's the problem here? Now the problem here is that when we do this, when we create a list containing an empty list or containing any object, then the same object gets replicated 10 times, but Python does not create copies. Now when you're working with numbers, it's fine, because when you're working with, let's say, the number 0, that's fine, because there's no internal structure inside 0, right? So there's nothing you can change inside the 0. It's a fixed value, fixed immutable value. So you can't really say L1 of 0 and change its value internally. What you can do is you can set L1 of 0 to another value. Let's say you can set L1 of 0 to 1. So instead of getting all zeros, you get all ones, but you cannot take the 0 and change something inside it. On the other hand, when you have an empty list here, so this is the same list that is showing up 10 different times. Each of the elements in the list, outer list, is simply a pointer to this same empty list. So what we can do is, since we can go inside this empty list and append something to it, so since this is the same object that we are seeing over and over, the 1 gets appended to the first list, and because the rest of them are the same object, we get back all ones inside here. Okay, so this is the reason we're spending time here is because this is a common bug that you may unintentionally execute. Whenever you want to create a list of empty lists, do not use this method. So what's the method you should use then? So here's one method you can use. Let's say you want to create a list of empty list of size 10. So you may be familiar with this object, this object called range, this function called range. What this does is, if you view it as a list, you can see that it contains all the elements from 0 to 9. Okay, now if you view the range itself, it simply shows you 0 to 10. But when you convert it into a list, you can see that internally it contains the values 0 to 9. Okay, so you can take this range and you can do something like this. Put this range, or put anything which is iterable inside these brackets, the list brackets, and then say for x in range, and simply put x. So what did that do? That did practically nothing. We simply took x from the range of 0 to 10 and returned x itself. So we created a new list like this. But suppose we multiplied it by 2 here, x by 2. So for each element in the range, we are multiplying it by 2. And so we get back a new list, which is 0, 2, 4, 6, 8. So this is, each element is the double of the elements that we have in the range. Now what we need is, we need just empty lists, right? So we can simply put an empty list here and we can ignore this value x that we get here. So now we get back a whole bunch of empty lists. So let's call this L2. And what we're now doing is, for each element in the range, we are creating a new empty list. So this is important. So now when you do L2 0 dot append 1 and then check L2, you can see that 1 was only inserted inside the first list. Okay, so watch out for this. This is something that you will probably go wrong with at some point. I've gone wrong many times. And one last change we can make here is, whenever you're not using a variable in Python, it's always a good idea to just call it underscore. You can still call it x, but sometimes somebody reading your code may not understand why you have declared a variable and not used it, and assume that maybe you've made a mistake. So just to make things very clear, it's always a good idea to make something underscore. It's also a variable name, a valid name, and mark something as underscore if it is not being used. Okay. So with that whole discussion about lists, we now know how to create a list of empty lists. So here you have a list of empty lists for underscore in range num nodes. So now we have created a list of empty lists. Then for each edge in edges, we need to do something. So we need to insert it into the right lists. Okay. Now what does for edge in edges look like? So let's see, for edge in edges, print edge. Okay, each edge is a pair. We already know that. And when you have pairs or tuples here, you can get the values out. So let's call them n1 and n2, node 1 and node 2. You can get the values n1 and n2 out like this. So now we can say print n1 and print n2. You can see that we are able to get values n1 and n2 out directly within the for loop. So let's call this n1 and n2. And now this is a much more Pythonic way of writing code. So one of the things that we are also learning is how to write code which is more Pythonic, or which is idiomatic in Python. And this is again something that will impress people when you use it in an interview or a coding challenge. So for n1 and n2 in edges, what we need to do is first we get self.data of n1. So this gives us the adjacency list for n1, the first node, and here we append the value n2, and similarly we do the same for n2, and we append n1 to it, and that's it. Now we've set up the graph. So let's create a graph g1. Let's call this graph1 maybe, and we simply invoke the graph function, and then we give it a number of nodes and the edges, right? So remember, self will be passed in by Python automatically as the object that is getting created. So the graph1 object essentially. So now the number of nodes is 5 and we have a list of edges. And let's see what graph1.data looks like. So there you go. You can see that 0 is connected to 1 and 4. And 1 is connected to 0, 2, 3, 4, and so on. Now while this is okay, it would be nicer to print it like this. So maybe let's see if we can print it like this. And the way to do that is to define a wrapper function. So we define a function called underscore repr, and it simply takes self as the input. And what we are going to do is we're going to call enumerate on self.data. Now what does that give us? Let's just check what enumerate on self.data gives us. Well, maybe before we do that, let's see what enumerate on a list gives us. Enumerate on a list gives us this object, but let's just get a value out of it in a for loop, because you can use an enumerate in a for loop and then just print x. So what enumerate gives us is it gives us the values from the list, but apart from those values, it also gives us indices. Okay, so you can get an index I and a value v out of enumerate. So then you can see that you can print both I and v here, and you will get back the same output. Okay. So what we can say is we can do enumerate self.data. Now because self.data contains these elements, so what we'll get back is we'll get back pairs. Let's see here. So we'll get back pairs 0, 1, 4, 1, 0, 2, 3, 4, 2, 2, 1, 3. Now this is starting to look a lot like what we want. Okay, so we'll just take enumerate self data, and we'll take these pairs. So the pairs will be a node, so node n and its neighbors. So we have the node n, so the node n will first be 0 and its neighbors will be 1 and 4. Node n will be 1 and its neighbor will be 1 and 2, and so on. And then, so for n comma neighbors in enumerate, what we'll do is we'll simply create a simple string. And here we're using string formatting. We're simply creating this string where we put this, here we place a placeholder where we put n, and then here we put a placeholder where we put neighbors. Again, let's just see what that looks like. And this is the best thing about Jupyter. While you're writing code, you can test your code right then and there simply by putting data into a new cell. So let's see graph1.data. So you can see here that now we have converted that enumerated list into a list of strings. So we have a string here. This is the string 0 pointing to 1, 4. This is the string 1, this is 1 pointing to 0, 2, 3, 4, and so on. But this is still a list of strings. What we need to return from the wrapper function is a single string. So the way to join them together, whenever you have a list of strings and you want to join them together, all you need to do is you say what you want to join them with. So we want to join them with a new line, and then call the join function on that string and return that, right? So that is our wrapper function, and we'll see its uses in just a moment. And similarly, we have another function called str. Now wrapper is used when we simply type graph1. So when we type graph1, this is the output of the default wrapper function. Now this will get replaced by the wrapper function that we are defining. But when we do str of graph1, or when we do print of graph1, or when we insert graph1 into a string, that is when the str function is used. Now we will simply use the wrapper representation. So let's just put self.__repr, and that's it. Okay. So let's see now. Let's type graph1 here, and you can see that now we have this representation printed using this wrapper function that we've defined. So we have 0, 1, 4, 1, 0, 2, 3, 4, 2 connected to 1, 3, 3 connected to 1, 2, 4, and 4 connected to 0, 1, and 3. Okay, so now we have a graph data structure that we've implemented using a class, so the adjacency list, and we have a nice way to print it out. And this is just good programming practice. Now you don't have to do this in a coding competition, or you don't have to do this. It's good if you do it in an interview, if let's say you're able to type this out quickly. But when you are working on your own problems, or on your own code, or on a project, always make sure that any classes you define have a good string representation, so that when you type the name of a variable, you understand what it represents and you don't have to spend time thinking about it. Make it clear to yourself. Okay. So that's the adjacency list, and we'll see how that is useful in just a few moments. But here are a couple of questions for you. Try writing a function to add an edge to a graph that is represented as an adjacency list. Okay, so here we've specified all the edges right in the beginning, but can you write a function add edge which takes a couple of nodes and it inserts an edge between those two nodes? And here's a hint, this code might be useful. So do try that out. Now here's another one. Can you write a function to remove an edge from a graph which is represented as an adjacency list? So here you may have to use the list remove functions to remove a particular element from a list, but these are two good exercises to complete here. Okay. Now before we continue, let's just save our work. And we know that this notebook is running on Binder, which is a free service. So we'll just save our work by running jovian.commit. And what that will do is that will capture a snapshot of this notebook, all the changes that you've made, and put this on your Jovian profile. Now this will go on your Jovian profile, from where you can continue running it, continue executing it from where you have left off. Okay. Now another common representation for graphs is called the adjacency matrix, which is slightly different from adjacency lists. In this case, for example, the same graph here is represented using this matrix. So what we do is we create a matrix of size n by n if n is the number of nodes in the graph. And then for each node, for instance, since we have 0 and since we have an edge between 1 and 2, so if you take the first row number 1 and column number 2, you put a 1 there. Otherwise, if there's no edge, for example, there's no edge between 0 and 2, you take the 0th row and column number 2, you put a 0 there. Okay, so you put a 1 wherever there is an edge between the 2 nodes, and you put a 0 wherever there isn't. And you can see that there is this reflexive property here, because 1 2 is 1 and 2 1 is also 1, because these are undirected edges. Now of course, if this is a directed graph, this would be different. Okay, so an exercise for you once again is to represent a graph as an adjacency matrix in Python. Shouldn't be too hard. All you have to do is, instead of, so in adjacency list we initialized a list of empty lists. Here you may want to initialize a list of zeros, a list containing lists of zeros. Okay, and then you may simply just want to fill in the 0 ones in the right places. Now adjacency matrices have their own benefits. Sometimes they are more useful. For example, when you want to immediately check if there is an edge between 2 vertices or 2 nodes, you can quickly look it up in the adjacency matrix. But in the adjacency list, you will have to get the list for one of them and then search through that list, which is fine for most cases, but in some cases you may just want an adjacency matrix as well. So that's one other way you can represent a graph, and that's an exercise for you. Okay, so now we know we've represented graphs, and now we can start looking at some graph algorithms, and probably the most common graph algorithm, something that you will ultimately get asked in one interview or the other if you're interviewing with a bunch of companies, is breadth first search. And breadth first search, well, this is what it looks like. So suppose you have this is a real world graph that we're looking at. So these are cities in Germany, and you can see that there are roads between these cities, and we have lengths of each road. Now we can ignore the lengths for now. What's important is that these cities are connected to each other, but not all cities are connected to all of them, all of the others. So starting from Frankfurt, you may want to find out which are the cities that you can reach from Frankfurt without stopping. So which are the cities that are one edge away from Frankfurt? And if you look at it this way, it turns out that Mannheim, Kassel, and Wolfsburg are the 3 cities that are one edge away from Frankfurt. Right? So if you start drawing this tree of sorts, so you will find that Mannheim, Wolfsburg, and Kassel are one edge away. Okay, then you might ask, which are the cities which are 2 edges away from Frankfurt? So now the cities that are, Mannheim is connected to Karlsruhe, and Wolfsburg is connected to these 2 cities, and then Kassel is connected to this city. Okay, so here you have these other cities, and then you might ask, which are the cities that are 3 steps away from Frankfurt? And that would be the remaining 2 cities, Augsburg and Stuttgart. Okay, now I'll let you think about this, but what you will find in this way, as you go step by step by step, like first you're finding all the cities that are 1 step away, so all the nodes that are 1 step away from a source node, then you're finding all the nodes that are 2 steps away from a source node. What this will give you is, ultimately you will end up, for each node you will find out how far away it is from the source, and that will be the length of the shortest path between the 2. Okay, and you can verify that. I'll let you think about it. For instance, if you see, you can go to Kassel by going this way from Wolfsburg to Nuremberg to München to Kassel, but that would not be the shortest path. But binary search, this is called breadth first search. Breadth first search will always discover the shortest path, because we're first finding all the nodes at distance 1, and then we're finding all the nodes at distance 2, and then we're finding all the nodes at distance 3. And if a node at distance 3 has a shorter path, then it would have been already found when we are finding nodes of length 1 or 2 or distance 1 or 2. Okay, so that's breadth first search. So here's one problem that you might face in an interview. Implement breadth first search given a source node in a graph using Python. Okay, and here is some pseudocode. So it's always a good idea to write or explain your approach in plain English before you implement it, so that you do not make mistakes while coding. So here is the pseudocode. So if you have to write a function BFS which takes a graph and a root or a source node, so first we say create a queue. So we're creating, and this is taken from Wikipedia. So first we create a queue, And what's a queue? Well, a queue is a very simple data structure. A queue is simply a list, and it follows a first in, first out policy. So when you have a list and you want to add something into a queue, it's also called enqueue, the enqueue operation. So when you want to add something into a queue, you add it at the end. Okay, so you have a list and then you simply keep adding things at the end. You just append things at the end of a list. But when you want to access something from a queue, you do not access any value directly. No, you always access the first available value. Okay, you access the first available value. In this case, what is called the value in front. And when you access a value, it gets removed. Okay, so in this way you can see that it implements the first in, first out policy. Like if first we enqueue 1 and then we enqueue 3 and then we enqueue 4 and then we want to dequeue, and when we want to dequeue, we simply get the first value that was inserted, which is 1. Then maybe we enqueue a few more numbers, 5, 2, 7. Then we dequeue and then we get back the first value that we had inserted, which is not yet dequeued. So then we get back 4 or whatever was the second value inserted initially, right? So that's a queue. And let's see how a queue is useful. So we create a queue and then we mark the label, we mark root. We label the root node as discovered. Okay, so we need to somehow track which nodes have been discovered or visited. And first what we'll do is we will mark the root node. So let's say we're starting from the node 3. We will mark 3 as discovered. So 3 is now discovered. And as soon as we mark something as discovered, we will enqueue it. Okay. Then while the queue is not empty, which is while we have not accessed all the elements in the queue, or while we have not dequeued all the elements from the queue, we dequeue an element. So we dequeue the first element which has not yet been removed from the queue. And if we are looking for a particular goal node, then we can simply end there, like we found that node. But we are not looking for a goal node, so let's remove this code. Yeah, so we get the first element or the first node from the queue, which is not yet dequeued. And then, so for example, initially we just have 3 in the queue. So then we get back 3, we get 3 back from the queue. Then we check all the edges for 3. So we check that 3 is connected to 1 and 3 is connected to 2 and 3 is connected to 4. So we see all the edges for 3. And if the other end of the edge, we check for each node, let's say the other end of this edge is 2. We check if 2 is not yet discovered or not yet visited, then we enqueue 2 into the queue. Similarly, we check for 1. And if 1 is not yet already discovered, we enqueue 1 into the list. Similarly, for 4, we enqueue 4 into the list. Okay. So we have dequeued 3. So 3 is no longer in the queue, or we've moved forward. We're no longer going to get 3 out of the queue. But now we've enqueued 2, 1 and 4. And 2, 1 and 4, we now understand they are at distance 1. So when we pick the next element of the queue, we dequeue the next element, the first in, first out, we get back 2. And then we mark 2 as visited. Great, now we visited 2. Oh no, we mark, as soon as we are adding something to a queue, we also mark them as visited, because we've identified that 2, 1 and 4 are all at distance 1 from 3 and we've added them to a queue. So we mark them as visited. Now, when we get 2 out of the queue in the next iteration, we check if there are any nodes which 2 is connected to, those are not yet visited. So 2 is connected to 1, but 1 is already visited. So there's no need to enqueue it again. And then 2 is connected to 3, but 3 is already visited. So there's no need to enqueue it again. And so we just move forward. Then we go to 1. And when we go to 1, we realize that 0 is not yet visited. So we enqueue 0. 4 is visited. So we don't enqueue 4. Okay. And that's how we proceed. So now what you should do is you should draw this on a piece of paper and work it out. Just write on a piece of paper what would be the first element that gets inserted and what will be the elements that we will insert into the queue, etc., etc. But this is the algorithm here. Exactly what we just discovered. So we dequeue in a vertex for all the edges that start from the vertex V or the node V. If the other end of the edge is not labeled as discovered, then mark it as discovered and enqueue it into the queue. Okay, so let's implement this. Let's see if we can implement this live. So we are implementing BFS, where we will get a graph and a source node. The first thing we need to set up is a queue. So the queue is empty. Then we set up discovered, and discovered will be false initially, and it will have the length. So we want to mark it false for all the elements. Okay, and remember, now we can use this notation here because false is an immutable value, so it doesn't matter. So we don't really need to use the range or the list comprehension notation here. Then here, let's come here. So we mark the label root as discovered. So discovered of source. Let's just call it root so that we don't get confused with the terminology. So we mark discovered of root as true. Great. Then we insert, or we enqueue the root. So we type q.append. Now enqueue simply means adding something to the end, and you know how to do that in a list. You simply call q.append. So q.append root. Great. Now Python lists by default do not support a dequeue operation. So what we will do is we will set up an index which will track the first available element in the queue. Okay, so whenever we dequeue an element, we will increase the index so that we move forward. So here we have the index idx equal to 0. So now while there are elements in the queue, which means while the next available index is less than the length of the queue, first we will get the current, we will dequeue. So dequeuing simply means getting the first in element, the element that was most recently inserted and has not been dequeued. So we get current is queue of idx, and then we can also increase idx. So as soon as we dequeue something, we update the index. So you can imagine that the index starts out here, and when we dequeue this or delete this, then we get that value out, and then we update the index to the next position. Okay, so now we have the current. So this is the dequeue operation. Then what do we have next? Now we want to check all the edges of current, right? So we are going to say for, so remember we have the adjacency list representation. So we will get for node in self.data current. So self.data current contains a list of all the nodes that are connected with the current node. So for node in self.data current, if not discovered node, so if we have not yet discovered the node, then we first mark it as discovered, and then we add it to the queue. So we do q.append node. Okay, so what you end up with this way is, first you have the source that got added to queue, and then we inserted all the nodes which were at a distance 1 from source, and then we insert, then if you follow the trajectory, you'll see that we will insert all the nodes that are at a distance 2 from queue, and so on, right? So ultimately, when we end up with this entire process, we will have the queue, and the queue will contain the list of nodes as they would be visited in a binary, in a breadth first search. Okay, so we can simply return the queue here. So let's try it out. So we have graph 1, and let's call BFS, and graph 1 is this graph. So let's grab this image as well. So let's simply copy the code for the image and come down here. Let's come down here and put the image here. Okay, let's call BFS on graph 1, starting at the node 3. Okay, of course, this should be called graph.data. So because graph is the graph that we're working with, so we need to check graph.data here. Okay, so we start out with the node 3, and you can see that 3 first causes 1, 2, and 4 to get inserted, and then 1 causes 2 to get inserted. Okay, now that's BFS for you. It's pretty much done at this point. But what would also be helpful is maybe to keep track of what is the distance of each node, right? So we can also keep track of a distance. So let's say we have a distance which we initially set to none, which we initially set to none. And we will track a distance for each node. So we have the distance here. And initially we are going to set the distance for the root to 0, of course, because the root is at 0 distance from itself. And the distance here means the number of edges, right? Then when something is discovered, so when we are discovering a node and that node was not already previously discovered, that means that the distance for that node is one more than the distance for the current node which caused it to be discovered, right? So the distance for example, if you're starting with 3, the distance for 1 is 1 more than 3, which caused 1 to be discovered. And the distance for 0 is going to be 1 more than 1, which caused 0 to be discovered. So that's the distance. Great. We've now also tracked the distance. One other thing that would be nice to have is what is called the parent. If you go back here, you can see that it would be nice to know what led to Karlsruhe being discovered. Was it Mannheim, Würzburg, or Kassel? So that we can work our way backwards and find a path from Frankfurt to Karlsruhe. Okay. So for that, what we can do is we can keep track of a dictionary, of a list called parent. Once again, we will have no parents by default, so parent none. And whenever we find a node and that node was not already discovered, then we can set the parent of that node to the current node which caused it to be discovered. Okay, and now we can return from the queue the distance and the parent. So let's see if that works. Okay, so it seems like now we have this is the order in which the nodes are being visited. So you can see that 3 is the first node to be visited, and 3 has, and if you want to check the distance of 3, you can see that the distance of 3 is 0. So this is distance is given in the order of the nodes, in the order of the original numbering of the nodes. So you can see that 3 is at a distance 0 from itself, obviously. Then you have 1, 2, and 4. Now, if you want to check the distance of 1, just check the index number 1 here. So 1 is at a distance 1. If you want to check the distance of 2, now that is at a distance of 1 as well. You can check here. And then you want to check the distance of 4. 4 is also at a distance of 1, right? So all of these 1, 2, and 4 are at a distance of 1 from the root node 3. And also you can see here that the parent of 1, remember these are 0, 1, 2, 3, 4. These are the indices of the nodes. So the parent of 1 is 3, and the parent of 2 is 3 as well, and the parent of 4 is 3. 3 itself does not have a parent, that's why this is none. And finally, the last node we visit is 0, and it is at a distance 2. You can see it is the distance here is indeed the highest. And the parent for 0 is 1, right? So because 1 was the first node that caused 0 to be visited, it could have been 4 too, but in this case, just how we implemented it, 1 was the first node which caused it to be visited. So 1 is the parent of 0. So if you now want to find the path from 3 to 0, you can look at the parent of 0, that would be 1. And then you can look at the parent of 1, that would be 3. And we are done. So we can work backwards from the target. We can keep checking the parent after parent of the target, and that will give us the entire path. So now we have the path, we have the distance, and we have the order in which these nodes will be visited. So you may get asked breadth first search in all these different variations, but roughly this is what the code looks like. And you can see here that the code is not too long. Now we have created all these additional lists, but you don't really need them. So the code is about 15 lines of code, 12 to 15 lines of code, not more than that. So that's BFS. Again, if you're working on a BFS problem, it always helps to first state it in simple words and work it out with an example, and then start coding so that you do not make mistakes while coding. Now, one question that you can work on is to check if all the nodes in a graph are connected. This may not always be the case. So for example, here you can see that all the nodes in the graph are connected, but sometimes you may have a situation where some nodes are not connected. For instance, if these edges 1, 1, 2 and 3, 2 weren't present, then 2 would not be connected to 0, and maybe 2 is connected to 5 and 6, etc. So here is one graph where not all the nodes are connected to each other. You can see that there are 9 nodes, but there are only 8 edges, and if you look carefully, you will see that 0, 1, 2, 3, 0, 1, 2, 3 are connected, but there is no connection from these nodes to 4. So 4, 5, 6 are then connected separately, and then 7, 8 are connected to each other, but not to one another, right? So can you use breadth first search to determine if all the nodes in a graph are connected? I would reckon yes. Look at this queue. Now this queue gives you all the nodes that starting from the source node are connected to the source node by 0, 1, 2, 3 or so many steps. If something is not connected, it will not show up in the queue. So you can simply check the length of the queue and see if that is less than the total number of nodes, and then use that to determine if all the nodes are connected or not. Now, another related question that you may get asked is to find the number of connected components in the graph. Now, what's a connected component? If you take a set of nodes that's connected, that's one component. And if you remove that, then you look at the next set of nodes that's connected, that's two components. If you remove that, then you take the next set of nodes that are connected, and that gives you the third connected component, and so on. So in this case, for example, you have, this is one connected component. You can check by drawing the graph, and then this would be one connected component, and then these would form one connected component. So 0, 1, 2, 3 would be one connected component, 4, 5, 6 would be another, and 7, 8 would be another. Can you find the number of connected components, or even can you list all the connected components of a graph using BFS? Yes, you can. Again, a very simple way to do it is just pick the first node, perform BFS from the first node. That gives you the connected component that contains the first node. Then find the first index, which is the first node which is not yet visited. Start BFS from that node. Now that will give you the connected component for the second node, and then keep repeating this till all the nodes have been visited. Okay. That's another question that you might get. Find the number of connected components, or list all the connected components in a graph. So BFS is a very versatile algorithm that can be applied to solve pretty much most graph problems that you may get asked in an interview. So do work on a few BFS problems and get some practice with it. Okay. Now, another way to work through a graph, to look through a graph, is what is called DFS. And this is the way in which you would normally explore a maze, where you start out in one direction and then keep going. So for example, we started out here and then we kept going till we hit an end, right? So you can see here that we kept going until we hit an end, and then we turned back and then we tried the next path, and then we turned back and tried the next path, and so on. So we go like this, and then we turn back, we try 5, go like this, turn back, we try 8, then we turn back, try 9, 10. Okay. That's another way to go about it. And in some cases BFS makes more sense, in some cases DFS makes more sense, and you can, in most cases, both of them work just fine for most problems. So you can implement either one when you are faced with a graph problem. So let's implement DFS, or depth first search. Okay. Now here is a depth first search. It's pretty straightforward. You pick a node and then you pursue the node, and then you next node, then the next node, and so on. Among the edges, you pick one node, and then once you've exhausted the path along one edge, you come back and try the next edge, and then you come back and try the next edge. So there are two ways to write it. There is a way to write it recursively, and then there is a way to write it without recursion. And I leave it as an exercise for you to write it recursively, but what we'll do is we will write it without recursion. And to write without recursion, we will use something called a stack. We will use a stack, and a stack is another data structure, very simple list-like data structure, but it's just like a queue, but it's different. Instead of being first in, first out, which is what we do in a queue, in a stack, we perform last in, first out. So here's how it works. You start with an empty stack. So you can think of it like this container or a cookie jar, and you start putting in things into that jar. You put in 1, and you put in 2, and you put in 3. So now when you have to remove an element from the stack, or you want to access an element from the stack, the only element that you can access is the element that was inserted most recently. So last in, first out. That's a stack. How is that going to be useful? It's pretty straightforward if you think about it, because this node, when you start from this as the source, you will add all these three into the, let's say you add these three into the stack. Now if you add these three, let's add them in this order. So you start with this node, then you add this, this and this. So you add these three into the stack. Then the last in value was 2. Okay. So then what you do is you extract 2 out, and then you insert everything that 2 is connected to into the stack. So you insert 3 into the stack. And then the last in value was 3. So you take out 3 and then you insert 4 into the stack. Then the last in value was 4. Then you take out 4 and you have nothing left to insert. So now this entire path has been exhausted. So then you end up with this 5. Now when you end up with 5, you can insert its neighbors 8 and 6 into the stack. And once 6 gets inserted into the stack, then you take out 6 and you put 7 into the stack, and so on, right? So you can see how depth first search is working using a stack. And roughly this is what the process looks like. You start a stack, it's empty. Push the current source, let's say the root node, which you are starting with, push the root into the stack. Now while the stack is not empty, pop the stack. So get the last in value from the stack, and that gets removed as soon as we call pop. Then if that node is not already discovered, then we mark it as discovered. And then for all the edges from V to W, so for all of its neighbors, we simply push them into the stack, right? So that's it. That's all we are doing. All of its neighbors which are not already visited, we can simply push them into the stack. Okay. So let's do that. Let's implement DFS. And once again, we will keep this picture in mind. So let me just grab this picture here as well. This is one of the nice things about Jupyter, that you can take these images and simply include them within your Jupyter notebook while coding, so that you don't make any mistakes. So let's say we're writing define DFS. And once again, let's assume that we are going to start from 3. And this picture is graph 1. So let's say we are starting from 3. So define DFS graph, and we have a root node that we want to start with. And the first thing we want to do is we want to create a stack, and you can use a list as a stack. You can simply add things to the end and then pop them from the end. So we create the stack, and then we find discovered. We mark discovered as false for every node. Len graph.data. Then we say stack.insert. So stack.append. So we simply add the number 3 to the end, or the root number to the end. So stack.append root, and then we don't mark it as discovered yet. Now this is the interesting thing in DFS, because remember, when you start out with 3, you don't want to mark 4, 1 and 2, all of them as discovered. You want to put them into the stack, but only when they come out you want to mark it as discovered, because you want to discover 4 and then you want to discover 0 before you discover 1. So that's why we put these into the stack, but we don't really mark them as discovered just yet. So that's why we're not marking the root as discovered. Then while len stack is greater than 0, we get the current value. So the current value would be stack.pop. So interestingly, Python lists do support a pop operation. So if you have a list and then you do l1.pop, you can see that the value v that you get from l1.pop is the value 2, and l1 now has the value 5,6. Okay, so you can use a dictionary, or you can use a Python list like a stack. In fact, we can even try append here to see the entire process. Let's say we are appending 3 and then we are popping 3. So we get back 3 and 562 remains. So we pop the current node and then we mark it as discovered. So we mark it as discovered here. Mark discovered of current is true. And we may also just want to store that this is the result that we have. So we may also just want to create a result list where every time we pop something, we are also going to add it to the result list. So let's say result dot append current, and then we are finally going to return the result. Okay, but here's the main logic. So for all the nodes in graph.data current, we are simply going to push those nodes into the stack. So we are simply going to say stack.append node. Okay, so what we do is we start with 3 and we then pop 3 and add it to the result, and then we put 1, 2 and 4 into the stack. We don't mark them as discovered yet. Then we pop 1 and then we put all of these 0, 2, 3, 4 into the stack. We don't mark them as discovered yet. We mark 1 as discovered now. Then we pop 0 because then we pop 4, not 1, because we insert 1 to 4. So 4 is the last inserted value. So then we pop 4, we mark it as discovered, and then we insert 0, 1 and 3. Now you can see that there is some repetition here. We're also inserting 3 once again. So just to avoid that, what we can do is we can say if not discovered node, only then add it to the stack, right? There's no point in adding something to a stack if it is already discovered. So now with that in mind, let's see, we start with 3 and then we insert 1, 2 and 4. Great. 4 is the last value inserted. So 3 is discovered now. 4 is the last value inserted. So we pop 4 and then we insert 0, 1, but we don't insert 3 because it's visited. So now 1 is the last value inserted. Then we pop 1 and then we try to insert some of these other values. It seems like everything is already inserted, so nothing will get inserted. Then the only thing that remains is 0. So we pop 0. Then we pop, once we've popped 0, we are going to pop 4. So the order in which we expect to see things is 3, 4, 1, 0, 2, I believe. So let's see. DFS graph 1 starting at the node 3. Okay, so it looks like we have 0, 1. So it looks like we made a mistake because we got some repeated values here. And that's because we may want to just check if not discovered current. We may want to just add this check and put everything inside this check so that any older values that have been inserted into the stack, which are already visited later sometime through another value in the stack, that gets ignored. So we end up with 3, 1, 3, 4, 1, 2, 0, right? So it goes like this. First we go from 3 to 4 to 1 to 2, and then we go from 3 to 4 to 0. So that's how it goes. Now, a challenge for you is to also implement distance. Now in this case, the distance will not really make sense because this is not the shortest distance anymore. So when you want to get shortest distance from one node to another, then you want to use BFS, not DFS, because if you track distance here, you may end up going by DFS 3 to 4 to 1 to 2. And that is going to give you a distance of 4, a distance of 3 to getting to 2, although the shorter distance is 1. So maybe distance doesn't make sense here, but what you may want to put in is the parent. You may want to track the parent for each node. Should be simple enough to do. Whenever you are popping something, you may just want to track its parent. Okay. That's an exercise for you. Another exercise that you can try is to write a function to detect a cycle in a graph. Now, when you're performing DFS, let's say you are going about performing DFS starting at 1, and you do this, and then you end up here back at 1, right? Because you go to from 1 to 2, 2 to 0. And when you notice that 0 points to 1, which is already visited, that gives you an indication that there is a cycle in the graph. A cycle is simply a path which leads from a node to itself. So 1, 2, 0, 1 is a path, and a path is something, a path is a sequence of edges. So 1, 2 is an edge, 2, 0 is an edge, and 0, 1 is the edge. So this is a path. But 1, 2 and 2, 4 is not an edge. So 1, 2, 4 is not a valid path, right? So cycle is simply a path that leads a node leads from a node to itself. So the challenge for you is to write a function to detect a cycle in a graph. Another challenge for you is to detect maybe the number of cycles in a graph. Okay, so that's another thing that you can try out. But we'll move on to another problem now. We'll talk about weighted graphs and get closer to that example of the railway map that we looked at initially. So here you have nodes. So you have nodes numbered from 0 to 8. So you have a total of 9 nodes. And you have edges too. Now these edges also have weights. And this could be distances, for example, the railway line, or this could represent any other information which is of value to you, right? So you decide what edge weights are, what they mean. In the abstract representation, we simply call them weights. So this is a weighted graph. And here is an example of how we can convey the information about a weighted graph. I can give you the number of nodes, and then I can give you a list of edges. So the first two elements of each edge tell you which nodes are connected, like the nodes 0 and 1 are connected here. And then the last element of the list, or the third element of the list, tells you if it is weighted, if there is a weight associated with the edge. Okay. So you have 0, 1, 3, and then you have 0, 3, 2. So 0 is connected to 3 and it has a weight 2, and so on. And you can verify that there are 10 edges here, and these are the 10 edges with the 10 weights. So that's one variation that we see in graphs. Here is another variation. This is called a directed graph. In this case, edges have a certain direction. So this corresponds to the example of hyperlinks, where we have pages, web pages on the internet, and one page can link to the other, but the other page may not necessarily link back. They may, in which case you may have a bidirectional edge, but in most cases there you would have a single unidirectional edge. So you have 0, 1, 1, 2, and 2, 3. Now directed graphs can be represented just the same way as undirected graphs. All we need to do is we need to provide some information that this is a directed graph, right? So you can simply say directed equals true, and that will simply, and once you provide all this information, that can then specify to the person who is going through this data that this is a directed graph, right? So here's how it's exactly the same as a normal undirected graph, but when we create the adjacency list, we can have a graph, we can have a node from 0 to 1, but we should not put 0 into the adjacency list for 1, because there's no way from there's no direct edge from 1 to 0. There's only a direct edge from 0 to 1. So keep that in mind. And similarly in the adjacency list, now you will not set both the values 0, 1 and 1, 0 to 1. You will only set one of them corresponding to the one direction, unless of course there is a bidirectional edge. Okay. And what we can do is we can even combine directed graphs and weighted graphs. So here's what we'll do. We will define a class which can represent weighted and directed graphs in Python. So we'll use it to represent undirected graphs, directed graphs, and weighted graphs, all of these. And we will take some information in the constructor to capture this detail. So let's create a class graph. Once again, we will create a constructor. Now this has the self, which is the object that gets created, always the first argument to any method in a class in Python. Then we take the num nodes, then we take the edges, and then we take a couple more arguments. We take a argument directed, which has a default value false, and we take the argument weighted, which has a default value false. Okay. And we're going to store the information self.directed. Let's store self.num nodes as num nodes, self.directed as directed, self.weighted is weighted. Okay, so now we come to the edges. So for edge, in edges, what do we do? Now an edge can either have 2 values or 3 values. If it is weighted, if it is unweighted, then it'll have 2 values. If it is weighted, then it'll have 3 values. So we need an if condition here. If self.weighted, then include weights, else work without weights. Okay. Now we may want to also, because we need to create an adjacency list, so we'll create self.data just as we have been doing so far. And in self.data, we will create a list of empty lists as we have done for underscore in range num edges. Now what we'll do along with self.data, we will also create something called self.weight, and self.weight will store for each corresponding value in the adjacency list, it will store the weight of the edge between the two elements. So for and you will see how it works in just a moment. Num edges. Okay. So we have self.data and self.weight, and this will make it easier. Another way you can do it is, instead of storing single values, you can store tuples inside self.data, which will correspond to the node and which will also contain the weight, right? So these are both ways to do it. I'm just doing it this way, but you can do it the other way as well, where you can store tuples directly inside self.data. But suppose it is weighted, then first we get the values out of the edge. So node 1, node 2, and weight from the edge. Remember, the edge is a tuple. And then first we set self.data node 1 and append to it node 2, and then we also set self.weight node 1. So at the exact same location where we have node 2, at the exact same index, we store the weight between the edge between node 1 and node 2, which is weight. Okay, so now we've stored one direction, which is node 1 to node 2. We may also need to store the second direction. So if not directed, so if the graph is not directed, only then we need to store the second direction. So we just say self.data node 2 dot append node 1, and then self.data node 2 dot append weight. Okay, and that's the case when it is weighted. If it is not weighted, well, the code is actually simpler. So we simply get node 1 and node 2 from the edge, and we say self.data node 1 dot append node 2, and then if not directed, so there's no weight here, so we simply check if the graph is not directed, self.data node 2 dot append node 1. Okay, so there's a bit of code here, but the code is again fairly straightforward. It's just a couple of things that we have to take care of, whether it's weighted or not, whether it's directed or not. But now that we've done this, we have a fairly generic representation for a graph, right? So now we can take this graph, and remember graph 1. So graph 1 had this information. So similarly, we can create this graph. We can use this graph class to represent graph 1, but we can also use it to represent one of these, which is a directed graph, a graph with weights, or a graph with directed edges, or a graph with both weights and directed edges, which we'll see in just a moment. Now, one thing that we'll also do here is create a nice representation. So let's just create a representation here. Now, I'm not going to get into the code of this, but roughly what we want is, while showing the graph, if there is a weight, we also want to show the weight. We'll show the weight alongside the other node. So let's see, we create a result. The result will be this, the empty string, and then we'll return that result. Then we are going to say for I comma nodes comma weights in enumerate self.data and self.weight. So now this is an exercise for you to figure out what exactly this is doing, and you can apply the exact same technique. Create a new cell and put this data into a cell, put the zip into a cell, and then see what that represents. If you're not able to, if it doesn't show something, then try converting it into a list or using it in a for loop, and then put enumerate around it and see what that represents, so that you understand what I nodes and weights represent. But I am simply going to write it here so that you see the final result. Okay, so let's take num nodes 1 once again, and edges 1. It was called num nodes and edges. So this was the initial data that we were working with. And let's create graph 1. And of course we want to do this only if it is weighted. So if self dot weighted. If it is not weighted, then we have a different case where for I comma nodes in enumerate self dot data, result plus equals okay, let's see. So graph 1, we are going to use the graph and we're going to pass num nodes edges, and by default weighted and directed are both false, so we don't need to specify them. And let's say graph 1, this should be num nodes. So you can see with live coding we always make mistakes, and it's almost always bound to happen. That's where Jupyter notebooks are very helpful, and it's always helpful to just test your function while you're writing it. Okay, so now we've created graph 1, and graph 1 you can see is an undirected graph. You can see that 0 points to 1 and 1 points to 0. Then let's look at graph 2. So we're going to grab this data. This contains, let's call this num nodes 2 and edges 2. This is a graph with weights. So now let's create a graph 2 graph, and here we pass in num nodes 2, edges 2, and weighted equals true. And let's say graph 2. Okay, there's a small change here. Yeah, so now you can see for graph 2, this was the graph we were looking at here. This graph, let's grab this image as well. Yeah, this is the graph that we were looking at, and you can see that 0 is connected to 1 and 3, and so 0 is connected to 1, 3 and 8, 1, 3 and 8, and there are also weights associated. So 0, 1 has the weight 3, 0, 3 has the weight 2, and 0, 8 has the weight 4, and so on. Okay, there seems to be something off here because 0, 1 only seems to be connected to 0. I think we may have made a mistake somewhere in the code. Okay, so we may just have to debug this code. It seems like we may have made a small mistake somewhere, because 0, 1, 1 seems to be connected only to 0, but 1 should also be connected to 7. I don't see why that did not show up here. This is the curse of live coding, and that's why I have created a I have some working code here. So I'm simply going to grab the working code right now. And we'll just replace that. But see if you can detect the bug in the code. Okay, we don't, the version I have does not require you to specify weighted, so we can simply skip weighted here. It detects automatically if the graph is weighted. Still something wrong here. Let's just quickly verify what's going wrong. So we are going through the list of edges here. And we are appending, maybe let's just print graph2 dot data. Maybe the issue is in the representation and not in the code. Graph2 dot edges. There seems to be some issue in the weight here. So we may not have inserted the weights correctly. I see. So this should be called weight. this should be called weight. And so should this be called weight. Oh, there was a syntax error here. Okay, I think we fixed it finally. Let's see, this should be called weight. So we have an edge here. We have too many values to unpack. We simply pass weighted equals true finally. And we need to make this a list. It's finally done. Some good hardcore live debugging, but we have this finally. And again, you get to see that when you're coding, you will make issues. You just need to, but if you have a clear idea of how you've written the code, it's easier to narrow down the issues by looking at the errors. But let's see this graph here. So we have 0 connected to 1, 3, and 8. And that's, you can see that here, 1, 3, and 8. A 0 connected to 1, 3, 8 with the weights 3, 2, and 4. Then we have 3 connected to 0, 2, and 4. So we have 3 connected to 0, 2, and 4. And we have 6 connected to 5 and 8. You can see 6 connected to 5 with the value 8. So great, we have now represented our graph properly. And this is why a representation is really useful, because now we can check if our implementation is correct. Before we go on and implement any graph algorithms, we can check if our representation is correct. Let's try one more. Let us also try this directed graph. So we're going to grab this code and put it here. Let's call this num nodes 3, edges 3, and directed 3. Let me grab this graph code here as well. We are working with this graph, and let's create graph 3. So for graph 3, we have graph and we pass in num nodes 3. We pass in edges 3, and you can verify that the edges are set up correctly. And we just specify directed equals true. So we don't really need this at this point. We can just say directed true, and weighted by default is automatically false. So we have graph 3 here. You can see that 0 is connected to 1 and 1 is connected to 2, but not to 0. So now we haven't inserted the opposite edge. And then 2 is connected to 3 and 4. Then 3 is connected to 0 and 4 is connected to 2. Great. So we've now set up another graph. And now here, similarly, you can check that if you have a weighted directed graph, the code is still going to work fine. Okay. So that's an exercise for you. And at this point, let us just save our notebook using jovian.commit. So the next question that we are going to look at is called the shortest path question. And this is really what we started out with. Let's say you have a bunch of nodes, and we have taken a directed graph here, but you need not have a directed graph. You can do this with an undirected graph too, and that will be an exercise for you. But you do need weights here. Now, whenever you're talking about shortest paths in terms of weights, that is when this algorithm makes sense. Now, if you do not have weights in the graph, then the shortest path can be found simply by performing breadth first search. Okay. So whenever you're asked to find the shortest path, the first question you should be asking is there a weight involved or are there no weights? Now, if there are no weights involved, then we're simply concerned with the length of the path, the number of nodes in each path. And in that case, you can simply perform a breadth first search. But if you have weights, whether it's directed or undirected, then the breadth first search alone may not be enough, right? Because it may turn out that certain paths. For instance, you go from 0 to 3. So you go, if you go via 0, 2, 4 and 3, the length of the path is 2 plus 3, 5 plus 4, 9. But if you, sorry, the total size of the length of the path is 2 plus 3, 5 plus 4, 9. But the number of nodes is 4, 0, 2, 3, 4. On the other hand, if you go via 0, 1, 3, in this case, the number of nodes is smaller. So there's just one in between. So 0, 1, 3, there's just 3 nodes total. But the length of the path is 14, which is far higher, right? So this could represent that you go to a far off place via a train and then take a train to something that was actually closer, even though there were more stops in a different route. Okay, this is what we're going to implement now. We're going to implement an algorithm to identify the shortest path from a given node to a given target. Okay, so now this time we are going to focus our search between a node and a target. So what is the shortest path in terms of the total weight of the path, not in terms of the number of nodes in the path, keep in mind. So what is the shortest path in terms of the total weight that we can find from a starting node to an end node? And roughly the strategy goes like this, and the strategy is called the Dijkstra's algorithm. Roughly the strategy goes like this. You have the source node, and the source node is at a distance 0 from itself. So there's nothing there really. But the first thing that we know, the first and the only thing that we know is that for one of the siblings, for one of the neighbors of the source node, the direct edge will be the shortest path. So for example, we have 1 and we have 2. Now you have direct edges from 0 to 2, and you have a direct edge from 0 to 1. 0 to 2 has the weight 2 and 0 to 1 has the weight 4. Now in this case, suppose we had an edge from 2 to 1 and that edge had the weight 1. Then you could go from 0 to 2 with a weight 2 and then go from 2 to 1 by a weight 1, and the total weight you would incur to get to 1 would simply be 3, and that would be smaller than the direct edge, right? So even if we are looking at direct connections of the route, we can't say that the direct edge is the shortest path except for one of the nodes, right? So if we just look at the node where the edge weight is the smallest, so you start at the root and you look at the edge with the smallest weight, then we can say for sure that the shortest path from the root to the next node, to the node 2, is the direct edge. Why? Because this direct edge is smaller than or smaller than equal to any other direct edge. So any other path that comes to 2 indirectly will contain another direct edge and then some other edges, right? So it will have a length greater than or equal to this direct edge, right? So that's the key insight here, that at every point you maintain a group of visited nodes. So in this case, initially just 0 is visited, and then you find the first node which is at the closest distance from any node within the visited group. Okay, so for example, if we start out at 0 and then we look at 1 and we look at 2, we see the smallest edge is 2. So we add 2 into our visited group because we know that this is the shortest path from 0 to 2. And at this point, now we take all of the siblings or all of the neighbors of 2 and update their weights. Now, because we know that 0 to 2 is a direct shortest path, so we can update the distance for 4. That 4 could be at a potential distance of 2 plus 3, 5. Or there could be a shorter path. So we've not yet added it. We'll just update 4. And similarly, if there was a edge to 1, we can update the distance of 1, and we can say that the distance of 1 is either 4, which was the direct edge, or it can be 2 plus 1 if there was a direct edge from 1. So now we'll get to know that 1 is at a distance of 3, which is smaller, right? In this case, it's not, but suppose there was a direct edge from 2 to 1 of weight 1, we would get to know that 1 is at a distance 3. So each time you add a new node, as you mark a node as visited, you update the weights of, or update the distances of all its neighbors, and then you simply find the next node with the smallest distance, right? So you will find that the next node with the smallest distance in this case is 4. And then you update the neighbors of 4. There's only one neighbor. The next node with the smallest distance is 3. You update the weights of 3 and so on. So that was shortest path in a directed graph. But here let's see a shortest path in an undirected graph where we have more such cases. So let's just watch this from the beginning. Let's wait for the animation to start again. So we start at 0. Then we check 2. Okay, we mark 2 as updated. Then we check 9. Then we mark 3 as updated. Then we update the distance of 14. But now we can see here that we have another path to go to 2. We go to 3. That's why we track that. And finally we get 2. We mark 2 as visited. Now we are considering 3. And using 3, we are updating the weights of all the other nodes. And then we are marking 3 as visited. Then we are using 3 to mark 6 as visited and so on, right? So at each point you have a group of visited nodes and you have distances for all the nodes that are connected with the visited nodes. And then you pick the first unvisited node with the smallest distance. Okay. Now let's read the algorithm. You first mark all nodes as unvisited and then you create a set of all the unvisited nodes and you call it the universal set. So a set of all the unvisited nodes is called the call it the unvisited set. Assign to every node a tentative distance value. Now set it to 0 for the initial node because the initial node is at a distance 0, and set it to infinity for all the other nodes. So we now set the distance to infinity because we've not yet visited the nodes. We don't know their distance. Then you set the initial node as the current node. So there is always a current node that we're looking at. In this case, we'll start with the initial node. Now for the current node, consider all of its unvisited neighbors and then calculate their tentative distances through the current node, right? So you have the current node and the current node is connected to a lot of unvisited nodes. And if we look at each unvisited node, we know the distance up to the current node because the current node is visited. And using that, we can calculate distances for the unvisited nodes. Now, if the unvisited nodes have distances set to infinity, then we know that the distance from the current node, for going via the current node is going to be smaller than the distance infinity that has been set. But on the other hand, if a distance has already been set for an unvisited node through some other node, then we can simply compare whether it is better to go through the current node or whether it is better to retain the distance that was obtained by some other node and just maintain that, right? So in this way, we simply update the distances of all the unvisited nodes that are neighbors of the current node. Okay. So for example, if the current node is A and it is marked with a distance of 6, and then there is an edge connecting it with a neighbor B, and then that edge has the weight or the length 2, then the distance to go to B through A from the source will be 6 plus 2, 8, right? So from the source to A is 6, A to B is 2. So the distance, if you want to go to B through A, will be 6 plus 2, 8. On the other hand, if B was already previously marked with a distance, right? So it was not visited, but it was just marked with a distance greater than 8. Then we know that we have found a shorter path via A. So we update its distance to 8. On the other hand, if we have a value, let's say the value for visiting B via another node D was 7. So we keep the distance as 7, right? So we are simply updating the distance. We are not yet marking we are not yet marking B as visited. Now, when we are done updating all the distances for the current node, then we mark the current node as visited. And of course, we remove it from the unvisited set, right? So we mark the current node as visited. Then a visited node will never be checked again, because once you have visited a node, you have found the shortest paths to it and you have used it to update the distances of all its neighbors. So you never need to visit it again. So then find the first unvisited node. Find the first unvisited node that is marked with the smallest distance, right? So now we have a bunch of visited nodes and then we have a bunch of unvisited nodes. Many of those unvisited nodes have been marked with a distance. So you simply get the first unvisited node with the smallest distance and make it the current node and then repeat the process. Okay. So you start out with 0. you see that you can mark the distances of for 1 and 2. So 1 gets the distance 4 and 2 gets the distance 2. Now then you mark 0 as visited. Now you see that the unvisited node with the least distance is 2. So you get 2, and then you mark the edges from 2. So you mark the distance for 4 as 2 plus 3, 5. And suppose 2 had a edge to 1, then you would mark the distance for 1 as 2 plus 1. If 1 was the weight of the edge, let's say, you would mark the distance for 1 as the minimum of 4 and 2 plus 1. So which will be 3. So you can mark the distance for 1 as 3. And that's it. And then you remove 2 from the unvisited set. Next, you find the next unvisited node, which has the lowest distance. So if this edge existed, that would be 1. But if this edge does not exist, that would be 4. So you get 4, and then you mark the distances for the neighbors of 4, and so on. Okay. So what we'll do is we will create this. We'll create this graph here, which contains. Okay, there should be a graph here that we can look at. Yeah, so we'll create this graph here, which contains 0 to 6, which contains 6 nodes, 0 to 5. This is the graph we are creating. Let's just put it here, this graph. Yeah, so this is the graph that we'll work with. And let's start writing our shortest path algorithm. So def shortest path. And we have a graph, and that's it. We have a start node. So let's call it source. And then we have a target node, that node that we want to get to. So we want to go from 0 to 5. And as soon as we mark the target node as visited, our algorithm is done, right? So first we mark everything as unvisited by setting visited false times len graph.data. So here we have marked visited. Then we have distance. So we take the distance as infinity. So here's a way to create infinity in Python. You just say float inf. And once again, we set all distances to infinity. Then we are going to maintain a queue. So because we have this first in, first out kind of structure, so we're going to maintain a queue. The first thing we'll do is we will mark the distance for the source node as 0. Then we can insert the source node into queue. So queue.insert or queue.append source. And then we'll set an index to keep track of what is the next element that we need to dequeue. So the first element is what we need to dequeue. So while index is less than 0 and not visited target. So while index is less than the length of the queue and the target is not visited. So what do we need to do? We need to get the current element from the queue. So we simply get queue of idx, and then we increment idx by 1. So we increment idx by 1 here. Then we need to take all the neighbors of queue, we also need to finally mark it as visited. So let's just put in visited current equals true here. But in between, what we need to do is we need to update the distances of all the neighbors. And then we also need to find the next node with find the first unvisited node with the smallest distance. Okay. So to update the distance of all the neighbors, we have written a function called update distance. So we'll call this function update distance or update distances, where we will pass in the graph, and we will pass in the current node, and we will pass in the distance matrix, the distance array, and we pass it in this way. And what update distances does, let's look at it here. And again, it's always a good idea to extract out specific pieces of logic into separate functions. So here we're calling update distances, where we have a current node, and then we have the graph, and then we have the distance. So we get the neighbors of the current node using graph.data. Graph.data current will give us the neighbors of the current nodes. Then we get the weights of the neighbors of the edges connecting the current node to its neighbors. So we get the weights as well. Now we go through each list of neighbors. So for I comma node in enumerate neighbors, and then we check, we get the weight. So now we have the node and we have the weight. So we have for each edge the node that it is connected to and the weight of the edge. And then we check the distance for the node. If the distance for the node, let's say, hasn't already been set, then it is infinity. So in that case, distance to the current node from the source plus the weight of the edge from the current node to the next node will be less than the distance. So if the distance of current plus weight is less than the distance, we simply update the distance of the node. On the other hand, if the distance of the node has already been set via some other node and that is less than the distance via the current node, then we do not update the distance. Okay, so that's all we are doing here. And we can ignore this for now, we'll come back to it. But this is performing exactly that update distances function that we talked about. Then next we want to find the next unvisited node. So here we have a function called pick next node, which has a list of distances and it has visited. So we want to track the minimum distance. So we first set a variable called minimum distance to the value infinity. And then we set a variable min node. So this is the node with the minimum distance to the value none. Then we iterate over all the nodes in that we have in the graph. So from 0 to n-1. And we check that if the node is not visited and the distance of the node is less than the minimum distance we've obtained so far, then we set that node to the minimum node and we set the minimum distance to that value. Okay, so we track the minimum distance, a running minimum distance, by going over all the nodes in the graph, and we keep track of which node has the minimum, which unvisited node has the minimum distance. So finally, what pick next node gives us is the first next unvisited node. Okay, so here we can get next node is pick next node, and we give it the distance and we give it visited. Okay, so now if there was a next node, it's possible that there is no next node because we've probably already visited everything that we can visit. So if there is a next node, then we enqueue it. So we say queue dot append next node, and that's it. That's pretty much it. So that is our shortest path algorithm. We create a visited list, we create a distance list, we create a queue where we will add things. So this will be all the nodes that we have visited. We'll go through this one by one, and the queue in order will give us a list of all the nodes in their order of distance from the source node. Now what we need to return here is we simply need to return distance of the target, since that was what was asked here. Let's also mark current as visited true here soon enough so that we don't end up visiting current again and again. All right, so let's run the shortest path algorithm then. Here we have a graph. This is the same graph that we see here. Now we can create a graph 7, and this is weighted and directed. So we will pass in graph, we will pass num nodes 7, we will pass edges 7, and then we will pass weighted equals true and directed equals true, and this is graph 7. Okay, this seems like it worked out right. 0 is connected to 1 and 2 with the weights 4 and 2 respectively, and 5 is connected to nothing. 3 is connected to 5, 4 is connected to 3. Okay, this looks fine. So now we can say shortest path in the graph from, let's say, from 0 to 5 in graph 7. And it says that the length of the shortest path is 20. So you have 2, 3, 4, 11. So 2 plus 3, 5. 5 plus 4, 9. 9 plus 11, 20. So that seems to be right. What would also be nice to get is just to see what that path is. And for this, we can introduce something called a parent. So here we can simply have another thing called a parent, which is set to none for each element. So visited, let's call this parent, and let's set it to none by default. And all we need to do is whenever we are enqueuing a node, we need to track why it got enqueued, right? So if a node is getting enqueued, then it is probably getting enqueued. Sorry, not whenever we are enqueuing, whenever we are updating the distance of a node, we need to track why its distance got updated. So inside update distances, whenever we update the distance of a node, we also set the parent of the node to that current node from which the distance got updated, right? And that's all we need to do. When we update the distance of a node, we need to track why did we update this distance, by which node did we come to update this distance. So this way we have now tracked the parent. And let's return not just the distance of the target, but let's also return the queue, and let's just return the parent for now. I think this should be fine. Okay, so now you have the parent for each one. So if you look at the fifth element, 0, 1, 2, 3, 4, 5, you can see that the parent of 5 is 3. So it seemed like we arrived at 5 from 3. And then if you look at the parent of 3, so 0, 1, 2, 3, the parent of 3 was 4. It seemed like we arrived at 3 from 4. Then you look at the parent of 2, it seems like we arrived at 4 from 2. Then you look at the parent of 2, and it looks like we arrived there from 0, and 0 was our source. So the path is, if simply going reverse, 0, 2, 4, 3, 5. Okay, and that's how you get the shortest path and not just the shortest path distance. Now notice that 0 itself does not have a parent because that was the source. Now you can repeat this with another graph. Let's say we take this other graph that we had. This was graph 2. So let's grab this image here. So let's get graph 2 and let's say shortest path, graph 2. And let's get the shortest path maybe from 0 to 7. So it seems like there are two paths. One goes via 1 and one goes via 6, 2, 3, 3, 2 and 7. So let's get the shortest path from 0 to 7. Okay, so we started out with 0. And we end up at 7. So 0, 1, 2, 3, 4, 5, 6, 7. So it seems like the parent for 7 was 1. And then the parent for 1 was 0. So it's clear that it picked the path 0, 1, 7. And the total length of the path was 7. Sounds good. We can try another one. We can try 2 and 8. So there are a couple of ways to go from 2 to 8. One is to go via 3. So you can go to 6 to there are 3 ways actually, but 6 to 6, you can go via 3, 0 and 8, or you can go via 3, 4 and 8. Let's see which one it picks. Okay, so now 0, 1, 2, 3, 4, 5, 6, 7, 8. So the parent for 8 is 5. Oh, sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8. So the parent for 8 is 4. So we came to 8 via 4. And then the parent for 4, 0, 1, 2, 3, 4. The parent for 4 is 3. So we came to 4 via 3. And then the parent for 3, 0, 1, 2, 3. The parent for 3 is 2. So we came to 3 via 6, via 2. So 2, 3, 4 is the path. And the length should be 8 plus 1, 9 plus 6, 15. Great. It seems like we figured out the shortest path once again. And this time this was an undirected graph. Okay. So as long as you have weights, you can apply this algorithm, and this algorithm is called the Dijkstra's algorithm. And that's it. So that's all we're going to cover today. Now, one thing that we have not looked at very closely is the running time complexities. So let's do a quick look at that. Let's do a quick look at, let's say, BFS, and see if we can identify and guess the running time complexity. And the full proof is left to you as an exercise. But roughly it looks like this. This is the main loop here. So where we are going through the queue. So the number of times this may happen is n, which is the number of nodes. And the number of times this might happen. Now for each node inside BFS, remember that we check a full list of nodes inside each node for BFS. So the number of times this may happen is equal to the number of, for each node, we may perform an additional number of steps equal to the number of nodes it is connected to, right? So if we have n nodes, so we have n while loops, and then if we have a total of m edges, and let's say those m edges are split across, if I count the number of edges for each node, the number of edges is e1, e2, e3, e4, and so on. And then the size of this loop for the node n1 is e1. The size of this loop for the node n2 is e2. The size of this loop for node n3 is e3. So if you add up the list of all the edges, e1 plus e2 plus e3 plus e4, so the total number of iterations inside this for loop turns out to be, you can see here, the total number of iterations inside the for loop will turn out to be the sum of all the adjacency lists. Okay, and the total sum of all the adjacency lists is equal to twice the number of edges. So you can see here the number of edges is 1, 2, 3, 4, 5, 6, 7, and you can verify that the number of elements of all the adjacency lists put together is 14, because each edge is represented twice, right? So we end up, if we have n, if we have n vertices and m edges, we end up with n plus 2m operations, right? So each of the n operations to start the while loop, and then each of the 2m operations, those are to iterate over each adjacency list, right? And now when we are talking about complexities, we can ignore the m. If m is the number of edges, we can ignore the factor 2 associated with it. So what we end up with is order of n plus m. So order of n plus m is the complexity of breadth first search. And now by this point, you should be able to just work it out by looking at the code. So do try it out. And if it's not clear, do ask on the forum. But order of n plus m is the complexity of breadth first search. And you will find a similar complexity for depth first search as well. Order of n plus m. For the shortest path algorithm, however, the complexity will be different, because in the shortest path algorithm, let's see it here. In the shortest path algorithm, what we do is we go over all the vertices. So we insert each vertex or each node into the queue once, and then we take it out once. So this contributes a factor n. Then when we are saying update distances, then it also contributes the factor m. But when we are picking the next node, we may revisit all the vertices once again, right? So here we are performing n operations inside when we are picking the next node. So that gives us order of n square plus nm. N square plus m. Yeah, something like that. So order of n square plus m, or n plus m into n. So those are some complexities that you will see reported for shortest path. And a way to improve this, a way to improve the picking of the next node, is to use what is called a min heap, so that you don't have to look through the entire list of nodes each time to pick the next node, but you can simply pick the next node in a very short time. So there's a data structure called a min heap that you can look at. The min heap is used to keep track of a bunch of numbers and easily track the minimum. So you can keep a bunch of numbers around in a binary tree like this, and the root will always be the minimum, and the numbers on the left and right will always be larger than the root. And then the same will be true for each subtree as well. and insertion into this heap is of order log n, and deletion into this heap is of order log n as well. And then the min max in this case, fetching the min or the maximum value is of order 1. So instead of looping through the entire list of nodes each time, what you can do is you can simply insert nodes into this min heap and delete nodes from the min heap when they become visited. And getting the next node is as simple as fetching the minimum value. Okay, so check this out. This is not something that will generally get asked. This is a more advanced concept. In fact, even the Dijkstra's shortest path algorithm, it's very unlikely that you will get asked. But do review it and do try as an exercise if you want to go further. Try implementing and improving the Dijkstra's algorithm using a binary heap. So that will take the complexity from m plus n times n to m plus n times log n. Okay, and that may be better. So do check that out. That's obviously going to be better for larger graphs. So do try to implement it. In fact, inside Python, there is a built-in heap called the heap queue data structure, and that will optimize the pick next node operation in the Dijkstra's algorithm. Okay. So that concludes our discussion of graphs here. There's a lot more in graphs. Graph theory is an entire course in itself. But since this course is particularly concentrated on data structures and algorithms from the perspective of coding interviews and coding assessments, this is as far as we need to go. So what you should do is you should practice more graph problems related to breadth first search and depth first search. That is really something that you need to become very familiar with. Breadth first and depth first search. And shortest path, maybe in sometimes some really hard interviews, you may get asked shortest path as well. So do familiarize yourself with that. But apart from that, you don't really need a lot more. But there are other algorithms. You can look at minimum spanning trees. You can look at topological sorting. You can look at connected components. That's another path. You can look at detection of cycles. And there's something called disjoint sets. So there's a huge number of topics that we can cover in graphs, but we'll stop our discussion here. So what do you do next? Review the lecture video and execute the Jupyter notebook. Complete the assignment and attempt the optional questions. And finally, participate in forum discussions. Very important. If you're stuck at any point, just go on the forum, ask a question. You can also share your code as long as it's not working to get help. And you can also join or start a study group to learn together with friends. And you can also find us on Twitter at JovianML and at AkashNS. And the next lesson is data structures and algorithms. In data structures and algorithms is Python interview tips, tricks, and practical advice. Thank you. Hello and welcome to Data Structures and Algorithms in Python. This is an online certification course being conducted by Jovian. Today we're on lesson 6, Python interview tips, tricks, and practical advice. This is the final lesson of this course, so I hope you're excited. My name is Akash and I'm your instructor. You can find me on @AkashNS. If you've been following along with this course and you have been working on the assignments, and if you complete a course project as well, then you can earn a certificate of accomplishment for the course, which you can find on your Jovian profile and also add to LinkedIn or download as PDF. So let's get started. First thing we'll do is go to the course website, pythondsa.com. So this is the course website, pythondsa.com. This is where you'll find all the information about the course. You can watch all the previous lessons, lessons 1 through 5, and you can also check out the previous assignments, assignment 1, 2, 3, and you have the course project as well. Let's open up lesson 6. Now on lesson 6, you will be able to find a video recording of the video you're watching right now. And here is the code that we will look at today. So today we'll do something different. We will simulate the experience of being in an interview. So while we have given you a problem solving template, and we recommend that you follow this template for any project or any notebook that you work on, any coding problem that you work on. And here on the problem solving template, we also have a method, something that we have been applying throughout this course. to different kinds of problems, different kinds of data structures and algorithms. But in an interview, obviously you will not have this template. So we'll see how to apply this method during an interview. And before we do that, let's revise the method so that we can recall it from memory when we are working on the interview problem. So here is the systematic strategy that we have been applying so far for solving problems. And do check out the previous lessons if you haven't seen them for examples of how to apply it in detail. So the step one is to state the problem clearly in your own words and identify the input and output format. And then the second step is to come up with some example inputs and outputs and try to cover all the edge cases that you can think of. So you want to think of all the possible scenarios, and that will help you write your code properly. Then step 3 is to come up with a correct solution for the problem and state that solution in plain English. And then step 4 is to implement the solution and test it using some example inputs. So this is important while you're practicing, but initially when you come up with a correct solution, it will be a simple solution, what is often called a brute force solution. And in an interview setting, you may not have the time to implement it from scratch, so you may skip if the brute force solution is too straightforward. Then step 5 is to analyze the algorithm's complexity and identify any inefficiencies in the algorithm. So what you can do in an interview is come up with a correct solution and describe it to the interviewer, and then analyze its complexity directly and start identifying inefficiencies, and then move on to apply the right technique to overcome the inefficiency. So this is where you need to identify which one of the techniques that you've learned in this course do you need to apply. Is this a binary search problem? Is this a divide and conquer problem? Is this related to binary search trees? Is this something that you can solve in a similar way you'd solve sorting? Is it important to look at the worst case or average case complexity? Is this a graph problem, or is this a recursion, or is this a dynamic programming or a memoization problem? So all of these things are something that you have to think about. And as you practice more and more problems, so for each of the lessons, if you try and practice about 5 to 10 problems, then you will start to recognize these patterns. And when you're on step 6, when you're trying to come up with the right technique to overcome the inefficiency, the ideas will automatically come to you. So practice is very important to succeed in step 6. And once we have determined how to overcome the inefficiency through the right data structure or algorithm, then we state that solution, implement it, analyze the complexity, right? So this is how a coding assessment or an interview should proceed for you. And let's pick up a coding problem and let's go from there. So here we have a coding problem, Python subarray with the given sum, and we'll read the problem. But before that, you can see that here this notebook is fairly empty. And what we're trying to do is we're trying to simulate the situation where you are on a call with somebody and they are interviewing you. And typically they would be using some platform like a Colab Edit, or maybe a platform where you can also run the code, or a platform where the question is somewhere, let's say on the right, it's already printed, it's from a pre-selected database. On the left and on the right, you can type your code and you can experiment with it. Now, we're not using any third platform here. What we'll do is we'll simply simulate that in our Jupyter notebook. Okay, so now we have this notebook running. We've clicked the run button on the Jovian notebook, and here we are. Now the question is, and this is a question that was asked during a coding interview for Amazon. Of course, a lot of other companies may ask similar questions too. Now you are given an array of numbers, and these numbers are all non-negative. You need to find a continuous subarray of the list which adds up to a given sum. This is how an interviewer might state the problem to you. And then they may also tell you an example. Sometimes they don't. And if they don't, it's always a good idea to ask for example. Now, you might sometimes feel that maybe if you ask too many questions, the interviewer might think that you don't know this or you're dumb in some way, but that's not true. It's actually the opposite. The more questions you ask, the better the interviewer is able to convey what they want. Right now they're busy, they're doing 5 interviews a day and they have their entire day's work. So sometimes they may just fail to state the question in its entirety. And if you don't ask for clarifications, you may assume the wrong thing and go ahead and implement something that's completely wrong. And that completely derails your interview, and trust me, it happens more often than you might think. Okay, so here is one example. So let's say if the interviewer did not provide an example, you can ask them, can you please give me an example for this problem? And then they come back to you and they say, suppose we have this array 1, 7, 4, 2, 1, 3, 11, and 5. These are all numbers and they're all non-negative. Some of these could be 0 as well. But suppose we have this array and I give you the number 10, that I want you to find I want you to find a continuous subarray of the list which adds up to the given sum, which is 10. So then they might also tell you that in this case, the solution is this subarray starting from position 4, starting from the number 4 and going all the way up to 3. And you can check that there are no other ways to create 10. Like if we took 1, 7, that would be 8, and 1, 7, 4 would be 12. On the other hand, 7, 4, 2 would be 12 again, but 4, 2, 1, 3 turns out to be 10. And once again, on the right, you will not be able to create the total of 10. So this subarray is what you have to return. Now, what does it mean to return a subarray? To return a subarray means to return the indices, which is the index of the starting term and the index of the ending term. And sometimes we know in Python, when we're working with ranges, typically the end index is outside of the actual data. So you could return the index of 4 and the index of 11. So that so the index of 4 is 0, 1, 2. So 2 is the index of 4, 3, 4, 5, 6. The index of 11 is 6. So if you return 2 and 6, and then I try to access the 2 to 6, 2:6 range of the list, then you will get this list 4, 2, 1, 3. And in fact, that's something that we can very quickly verify here. Let's say L1. So you have 1, 7, 4, 2, 1, 3. Now, if I say that the start index I and the end index j are 2 and 6 respectively, and you can see L1 of 2 to 6 is 4, 2, 1, 3, right? So although j is outside, so that doesn't get included when we put it as a range. And then we put in 4, 2, 1, 3. And you can also verify that the sum is 10. Okay. All right, so that's the problem. Now I've explained it to you in a lot more detail than an interviewer would, but this is the process that you have to apply in your own mind. And sometimes what you can also do is you can repeat the problem back to the interviewer. That's a great idea. They've stated the problem to you. They've maybe given you an example. Now you state the problem yourself in simple words. Remember, that was step 1. So in the same way that I just have, you can state the problem, and then you have to figure out what are the inputs and the outputs. So the input, you have an array, or array is also a list in Python. So let's say ARR 0. Let's make this an example first input, and that would be 1, 7, 4, 2, 1, 3. And then the target, so your target sum is 10. So that's the input here. And then the output that we want is, so this is the output 0. That would be 2,6 as we've just verified. So this is the input and output format. Always makes sense to just create some variables for that before you start coding. The next step is to think of what are all the cases that a function should be able to handle. But actually, before we do that, we should also write a function signature, because we know what the input looks like. We know what the output is going to look like, and we know what the function should look like. So we can just say def, and let's call this subarray sum. And it's going to take an array, it's going to take a target, and there's going to be some logic inside it. Okay. All right. So that was step 1. Sorry, I forgot about the function signature, but it always helps to just write the function signature, because if you've misunderstood the problem still, the interviewer can immediately correct you and tell you, hey, but you haven't taken a certain input, or you've assumed an input which I have not provided. Okay. All right. So now we have the function signature. Now step 2, remember step 2 was come up with an exhaustive list of test cases to test the problem. So you can do this in comments. You can just create some comments and you can say, I'm thinking about the problem and I'm just trying to think what are all the cases we need to handle. And this is a great quality. This is not something people do often, but they should, because this indicates that you are doing what is called test-driven development, which means you are thinking about all the ways in which your code might be used and accounting for those before writing the code. So kind of working backwards, and it's a very useful way to avoid errors. So now the first one could be a generic array where the subarray is in the center, somewhere in the center, right? So which is what we have already seen here. Now the subarray could be in the center, or the subarray could be at the start, or the subarray could be at the end, or it's possible that the subarray, there is no such subarray. So there's no subarray which adds up to 10. You may also have the situation where you have a few zeros. So you have a few zeros in the list. That's one option. Here's one thing that can happen. This could be that there are multiple subarrays with the same sum. Now this is where you might want to just clarify with the interviewer, hey, what happens if we get two subarrays which add up to the same number, the target? And the interviewer might say, find the shortest one, or find the first one, or find any one. But it's always good to clarify that. Next, one option could be that, or you could also ask them what happens if there is no subarray that adds up to 10, and then they may tell you can return none, or you can return -1, or whatever it is, or assume that there is always a subarray. So that will help you write your code. And then you may have to work with the empty array. You may also have to work with the subarray is a single element. And whenever we say array, we also mean list. In Python, they're practically speaking the same thing for our purposes. Okay, we've listed quite a few test cases, and in that process, we've come across a few more questions which we've clarified. So now we're ready to start solving the problem. Now, at this point, what you may want to do is maybe just ask for a couple of minutes and keep a pen and paper close to you. So I'm going to use this tool instead. Yeah, so I'm going to use this tool instead. So keep a pen and paper close to you so that you can work on this problem. Now, let's come up with the simplest possible solution, right? So we have about 2-3 minutes to come up with a solution. And often the simplest solution is pretty obvious. So in this case, one simple solution could be, if I could simply try every subarray, then I will find at least one if that adds up to 10, if there is one. So all I need to do, now each subarray is defined by a start index, that is where the first element of the array is, and then an end index. The end index is just next, the next index, the first index which is not in the array, right? So that's how we defined a subarray, remember? So all we need to do is try all such values. So all such values I comma j, where I goes from 0 to n-1, and where j goes from, remember you could start out with the empty subarray, so which means j also has the value I. So here we are saying I and j both have the value 2. So L1 of 2 to 2 becomes the empty array. So j goes from I to all the way beyond the last element, which means if the last element's index is n-1, so j can go all the way up to n. All right. So I goes from 0 to n-1, and j goes from I to n. And each time we start at an I and we check each j. So we check j equals 0 and j equals 1, j equals 2, j equals 3, 4, 5, and so on. Then we move I again, and then we start over again, and then we say we start with j equal to 0, j equal to 1, j equal to 2, 3, 4. Okay. And we keep doing this till we find an array, and we've exhausted. This way we'll test all the subarrays so the problem is solved. So that's the brute force solution. And what you should do first of all is explain that brute force solution. It may seem that this is an obvious solution. What's the point of explaining it? But do mention it, because at this point the interviewer knows nothing about you. So they don't know if you can even come up with a solution to the problem, right? They're trying to assess, can you think about problems? And they're trying to assess, can you write code? Now, if you don't tell them the brute force solution, then they don't even know if you figured out the brute force solution. So do tell them the brute force solution. And generally you do not have to code it. you can do the analysis in your memory, in your mind, and you can sort of write the code in your mind, picture the code, and based on that come up with the complexity analysis and directly say that the brute force algorithm will have such and such complexity. Okay, now we will just write the code right now just to be very clear about it, in case you're not yet clear on how to write the code. But in an interview, this is the part which you can skip in the interest of time. So def subarray, I think it was called subarray sum. Subarray sum, and let's call this subarray sum1, the first approach that we're taking. Here we have array 1, and that's it. We have array, and then we have our target, and we're saying, remember that start I from, so I goes from 0 to n minus 1. That was the first thing. So for I in range 0 to n minus 1, and what's n? Well, n is simply the length of the array. Then j goes from I to n. Oops, so I made a small error here. This should say 0 to n, because even in a range the last value is not taken. So j goes from 0 to I to n. So for j in the range I to, this should be n plus 1 then, because we want j to go all the way up to n. Okay, and now we simply check if the sum of array I to j, right? And we've seen this array I to j is going to give us all the indices starting at I but ending just before j. So if the sum of array I to j equals target, then we found the answer, return I comma j. That's it. So check if subarray sum equals target, and if not, let's just return none. Maybe this is what we agreed, but let's return none, and that's it. So that's your code. It's about 1, 2, 3, 4, 5 lines of code, maybe 6, but that's a brute force solution. If it's really short, it doesn't hurt to write it, because then it's going to sit there, and at least as a reference you have it. But it's something you can discuss with the interviewer. I mean, if you are clear about the brute force solution and you can tell its complexity, then you don't have to write. One other tip is, whenever you're coding, it's always helpful to simply add a small comment above, so that even if the interviewer is not able to follow your code, they can just follow your comments and they can tell if your general strategy is correct, right? Once again, reading code is hard, and especially when you are not familiar with the coding best practices in the industry, the code that you write is sometimes difficult to read. So while you learn how to write good code, in the meantime, it always helps to just mention comments. Makes their job easier, makes it easier for them to evaluate you. Otherwise, you may spend 5 to 10 minutes talking about something in your code which either they misunderstood or you made a typo, etc. Okay, so we have here the subarray sum1. We've implemented the brute force solution. Maybe let's also check out some cases and see if this brute force solution works correctly. So in an interview, if you have the ability to run the code, you can just run a few samples. So let's say I simply take array 0 and target 0, and you get the value 26. And remember, output 0 also has the value 26. So great, it seems like our technique worked. Let's test a few more cases just to be sure. Subarray at the end, subarray at the start. Let's see if we can fix that. So here is array 0. Now if I take this, remember 4 to 1, 3. Oops, I think I didn't complete it. Let me also put in 11,5 here. Yeah, so remember 4 to 1, 3 is the solution. Now if we simply take 4 to 1, 3, 11, 5 and call sub array sum and put in this number here and put in, once again, the target 0 was 10. Oh, this should be somewhere some 1. Okay. Yeah, so now you can see 4 to 1, 3 is 0, 1, 2, 3, which is the range 0 to 4. So it seems to have worked correctly. Let's do the same thing. Now this time let's put this at the end. So 1, 7, 4, 2, 1, 3, 11, 5. This works fine too. 2, 6. Let's try another one. Let's try maybe 17, and that probably cannot be found. Oh, it can. 1, 2. Let's see. 1, 0, 1, 2, 3, 4, 5. Probably the sum of all of these 4 plus 2, 6 plus 4, 10. Okay. Now maybe there's a problem here because it seems like 17 is not the right sum. So you have 1 plus 7, 8. And 8 plus 4, 12. 12 plus 2, 14. 14 plus 4, 18. Okay, so this seems like a mistake then. And we can even check this out. So we have L1. That's that. Let's call that L2. L2. Oh, it says 1 to 6. I think I misread it. So we are ignoring the 0th element. So this does add up to 17. Okay, so 17 does show up. Let's try 18, which takes up the entire array. Works fine. Let's try maybe 4, which should just take the single number. So that works fine too. Let's try 19. That should be none, none. Okay. So we've tested this extensively, and overall our solution seems correct. This is the process. Whenever you write any code, you should also test it out, and it also gives more confidence to the interviewer. But if you do not have the option to test it out, if you're not able to run the code right now, then simply walk them through an example yourself. Like look at this example and then walk them through the example. Okay, so now we have the brute force solution. The next step is to analyze the brute force solution. Now let's analyze it. So you have here one for loop, and we know that counting for loops helps us count the number of operations. Then we have another for loop. So one for loop can go from 0 to n. So this may run n times. Then we have another for loop which goes from I to n plus 1. Let's approximate here and say that it can run at most n minus 1 times or n times. So n, and inside each of these up at most n. And then inside the second for loop, you have the sum. So this is very important. Now always carefully observe the operation inside your for loop. So you have a sum which can be on an array of I to j. Now remember, I can be 0 and j can have the value n. That means in the largest array that you can work with will have approximately the size n as well, right? So you have n, and inside each of those you do n other loops, and inside each loop you do n additions, right? At most n additions. So that roughly gives you that this is going to be n times n times n. So this is going to be an order n cube solution. Okay. So if you are able to arrive at the order n cube solution, the order n cube complexity without implementing the solution, great, you have learned it. But if you're not able to arrive at the order n cube complexity for the brute force solution, then you probably need a little more practice, because this should become second nature to you. Just looking at a problem, identifying the simplest solution, and then finding the complexity of the simplest solution. Okay. All right. So now we have implemented it, tested it, and we've identified the complexity. Remember the next step: find the inefficiency and overcome that inefficiency by applying the right technique. So let's find the inefficiency then. Here we have, let's say we are at this position. So let's say you are looking at 742. Let's say I has the value 1. So you start out with I equal to 1 and j equal to 1 in the inner loop. Then what we do is we increment j by 1, and then we calculate this sum, and this sum is 7. Then what we do is we increment j by 1 more, and we calculate this loop, and this sum is 7 plus 4, 11. Then we increment this window once again, and then we calculate this sum, and that is 7 plus 4 plus 2. So 7 plus 4, 11 plus 2, 13. And then we move this, and then we check it again. So we are doing this over and over and over many times, right? Each time we are doing 7 plus 4 plus 2 plus 1 and 7 plus 4 plus 2 plus 1 plus 3. That seems like a lot of additional work. Maybe we can just avoid that. What we can do is when we start out with a j, we can keep a running sum, and each time simply before incrementing j, add this upcoming element, which is the jth element, into that running sum, right? And that way we don't have to do that entire sum inside each of the inner loops. So that's one optimization, and this is how you should explain it. That's one optimization that I have come up with. The second optimization that we can come up with is that the moment the running sum that we're calculating, the moment the sum becomes greater than the target value, we can skip all of these, right? So we know that 7 plus 4 is greater than 10, and we know that the array only contains non-negative number. So what that means is 7 plus 4 plus any of these numbers is always going to be greater than 10, right? You can see this, the number is not going to decrease if we keep adding positive numbers. And so as soon as the running sum crosses this value, we can break out of the inner loop. We do not need to continue and look for higher values of j. So two optimizations. Helps to just write them down. Maintain a running sum so that you don't forget it. And second optimization is when sum exceeds target, break inner loop. Okay, so now we have applied an optimization simply by just looking at the data. In a lot of cases, it's very straightforward. You don't even have to apply any special technique. And in this case, we found these couple of optimizations. So let's apply them. So what we'll do is we'll define def subarray sum2. And here, once again, we have the array and we have the target. And this time we get the length of the array. And now once again, I goes from the same value. So I goes from 0 to n minus 1. Nothing changes here. So for I in range 0 to n minus 1. Now here is where we want to start a running sum. So s equals 0. This is our running sum. Then for j in range, remember we'll start out with I and we'll go all the way. Well, I keep making these mistakes all the time. And by the way, these are called off by 1 errors. Here what we did was I wanted to go till at the address n minus 1, but because ranges do not include the final value, I put in what I put in. N minus 1 was wrong. I should be putting in n. And I make these mistakes all the time, even after many years of coding. So always watch out for off by 1 errors. Anyway, so j can take the range of 0 of I to n. So here we should put in n plus 1. And now first we want to check if the running sum is equal to the target, right? So assume that we've been calculating the running sum step by step, and we'll write and at this current point the sum has become equal to target. If the sum has become equal to target, then we simply return I comma j, because this sum includes the sum from index I all the way up to just before j. So initially the j also has the value I, so the sum is 0, which makes sense. But if that is not the case, we check if it is greater than the target. So is it possible that our sum has already exceeded the target? In that case, we don't need to continue this inner loop. We can break out of this inner loop, and the way to do that is by simply typing break. And then if neither of these held true, if neither of these was true, so which is that the sum was not equal to the target and it was not greater, that means it is still less than the target. So that means we need to then add array of j into the sum. So we can say sum plus equal to sum plus equals array of j, which is the same as sum equal to sum plus array of j. In any case, array of sum plus equal to array of j. So we have added the jth element. Now remember, if this is the pointer j, we added the jth element, and then we will set j to j plus 1. That will happen automatically when we come into the next iteration. And the next iteration will once again check if the sum is equal to the target. If it is equal, we return I comma j. Otherwise, we check if it is greater than the target. If it is so, we break. If it is still less, we move j once again. So we add 1 and then we move j once again and then we check again. Right? So that's our running sum. Looks good. Now, once again, if it was found, it would have been returned somewhere here. Since it seems like it was probably not found. So if we come to the very end, so here we return none. Okay. And once again, let's test it out. So let's try subarray sum 2. It gives you 2, 6. Subarray sum 2 of none. Okay. Seems like there is an issue here. Yes. So this is why you need test cases. So it seems that array j took up an invalid value. So why is that? Well, that was because j can go to the point of n. So the maximum value j can take is n. So which means that you have already arrived at this position. So now you can no longer increase the sum further, right? So if you've arrived at this position, but you've still not reached the total of 10, then that means you may need to increase it further, but you can't increase further. So there's no number here to add. So what we should do is we should here add a check if j less than n. Since j can go all the way up to n. And that's it. So we had a small bug and we fixed it. Now, again, this is something that you should work out for yourself on pen and paper. So even while doing the optimization, you can ask for a couple of minutes, play around with it on pen and paper, write a few examples, relax. You can even take up to 4-5 minutes. And if you're not getting any ideas, you can simply talk to the interviewer. You can speak out loud, explain your thought process. And in a lot of cases, they will give you a hint because they want to see you succeeding. Okay. So now this is the second implementation. Let's see. Okay, this time it worked. None. 4213. Let's put in 10 here. This should give you the value 2,6. Let's put in this. So that's 0,3. Let's test this out too. So that's 0,4. Yeah, 0,4. So it seems like it's working just fine. Yeah, so seems like this is working pretty well. So now we have the second optimized solution. So let's look at the optimized solution and analyze it. So we have one loop and then we have a second loop. These two are the same, but inside the second loop, we are simply doing a constant operation. We are just doing some comparisons and one addition, not up to n additions. So the complexity goes from order of n cube to order of n square by maintaining a running sum. Great. Now, at this point, when you have described the solution to the interviewer and maybe also coded it, you might ask them, is this good enough? And they can see that you've thought about it, you've found the solution and you've tested it and it tests well. And at this point, they may just say, yeah, I'm happy with the solution. This is good enough. Or they may say, can you do better? Now, when they say, can you do better? Most of the time it suggests that there is a better solution. So let's see, let's think about it a little more and let's see if there is a better solution. Now, to can you do better, we apply the exact same technique. We have analyzed the complexity and now we need to look for inefficiency. Okay. So now we have removed the inefficiency on this side, which is as we move j, that is when we reuse the previous sum to compute the next sum. So we've removed the inefficiency on this side and we've also added this condition so that j only goes up to a certain point. Now, of course, in the worst case, j may always go up all the way to the end, but at least in a lot of cases, j will not go beyond a point where the sum becomes larger than the target. So these are good optimizations, but what about I? What about the left window? Now look at this here. Now when you have 7, 4, or let's start out all the way at 1. So we have 1. So first we start out with the empty subarray that has the sum 0. Then we increment j. So now the sum becomes 1. Then we increment j. Now the sum becomes 8. Then we increment j once again. and now the sum becomes 12. Okay, the sum has become 12. Now that's a problem. So what do? What we are saying is we will take I and set it to the next value, and then we'll bring j back to 0 or back to the value I, so that we start with the empty subarray once again. So now when we do 7 and when we, so that just has the value 7, and when we do this, we have to add up 7 plus 4. Now here's something that we could have done instead. Now as soon as the value became larger than the target value, we could have simply moved this here. Does that make sense? Let's think about it. So till this point, this total was less than 10. As soon as we added this number on the right, this total became more than 10. Now we know that this total became more than 10. That means that if we slide this window, if we slide the left window forward one step, then the total may become less than 10, right? It may still stay larger. In this case, it stays larger, or it may become less than 10. So if the total now becomes less than 10, then we can once again move this. But the total has not become less than 10, so we will move this instead. So now the total again is less than 10, so we can once again move this. And now the total is still less than 10, so we move this. Now the total is still less than 10, we move this, and we encounter 10 here. But suppose we had not encountered 10, suppose this number was 4 instead, then what we would have to do is move this, right? And now the number becomes less than 10. So we always try to maintain a window of size less than 10. The moment the window becomes greater than 10, we keep trying to reduce its size further to less than 10, right? Or exactly 10 as well. It's possible that the size may become exactly 10 and then the problem is solved. But we keep trying to reduce its size to a value till it becomes less than 10. So to revise the algorithm, we start out with both I and j at 0. Then we increment j while the running, now we have a single running loop and a single loop essentially. So we increment j while the sum is less than 10. The moment it becomes greater than 10, we start incrementing I. The moment the sum becomes less than 10 or less than target, we start incrementing j. And if we encounter the point where the sum equals 10, we have found the answer. So that's the algorithm. So let's write it. Subarray sum 3. Now this is the array target. Now we have I, we have j, and we have sum. All of them, let's call it s, because sum is a reserved word in Python, an existing function. So all of these have the value 0. Then we say while I is less than len array, let's call that n. So let's create n equal to len arr. I is less than n and j is less than n plus 1. Remember, because j can take the value n as well. It is the exclusive end index. Now at this point you want to check first. So if the sum s, the current sum, running sum, is equal to the target, then we simply return I comma j. If sum is less than the target, then we simply increment j. Okay, so now we can move the window forward. So we are incrementing j if the sum is less than the target. So we increment j, but before we increment j, we should add the jth element to maintain the running sum. So here we say s plus equals j or array of j. And remember, j can take the value n as well. So that's where we do this only if j is less than n, if there is indeed an element for us to add. This is an error we faced last time, and you will discover this when you write the test anyway. And then we say elif s is greater than target, and we can also just say else here, but just for clarity, let's say elif. In this case, what we want to do is we want to move I forward. So suppose we end up in a situation like this, then we want to move this forward. For that, we need to subtract s array of I first. So we say s minus equals, which is equal to s minus which is the same as S equals S minus array of I. And then we increment I. So we move the left window forward as well. So we then repeat this. So we first move J to a point, then we, as soon as we cross the target, we start increasing I, and then we keep doing that till we match the target. And then finally we return none, comma none if we have not found it. So that's our subarray sum 3. This seems like the most optimized solution, and let's test it out. So here we have subarray sum 3. And let's test subarray sum 3 here as well. Seems like it worked. Let's see. So if you put in 10 here, you get 2, 6. Let's say this is 4213, 0, 4. Let's put in 12 here. That doesn't show up. Let's put in 17 here, 0, 5. 13, 1, 5. Let's try 19. That's 3, 6. Let's see, 1 plus 3 plus 7 plus 9. Yeah, that has the value 19. Let's throw in a 0 there and see if it works with zeros. That's 3, 7. Works fine. And let's see if it doesn't work out. Yeah. Okay. Great. So this solution is correct too. Again, if you don't have the option to run the code, you can simply pick one example and walk through the working of the example. Now we have subarray sum 3, and once again we are ready to analyze the complexity. And in this case, the complexity would be, this is somewhat tricky, this is a little bit unusual because there is a while loop with 2 variables. But remember that in each while loop, either we exit, which is the best case, so we can ignore that, or we either increment j or we increment I, right? So we increment j or we increment I. And if we increment, so j can go from the values 0 to n, and I can go from the values 0 to n minus 1. So the total number of increments we can do is the sum of the number of possible values of I and number of possible values of j, right? Remember, this is not a product this time because you do not have a nested loop. So for each value of I, you're not doing this. Rather, you are incrementing each one and I only one of them each time. So the sum of total number of values I can take is n. The total number of values j can take is n plus 1. So the total becomes, the number of iterations becomes 2n plus 1. Now, of course, there's the count. You can verify that a constant amount of work is being done here. So we finally end up with the conclusion that this is an order n algorithm. Okay, so this is finally an order n algorithm. So this is a good example of a problem where the step-by-step solution, coming up with a simple solution and then thinking about the inefficiency in the problem and then applying, in this case, just common sense to solve the inefficiency step by step, leads to the perfect solution, and a very good solution in fact. So you start out with an order n cube solution. The order n cube is going to be pretty slow when you start hitting, let's say, even 1,000 elements. If you have 10,000 elements, it will take forever. It will take maybe an hour or so. If you have 1,000,000 elements, it will take hundreds of years. On the other hand, order n can work fine all the way up to 1 billion elements, right? So there's a huge difference between the subarray sum 1, 2, and 3. Subarray sum 3 can work instantly for 1 billion elements. Subarray sum 1 will take forever, even for 100,000 elements. And subarray 2 is in between, and you can do the math. And this technique, where you can almost certainly tell what the next step is. So this was not really related to any of the algorithms or data structures that we have talked about. This is what is called a greedy approach, where you know some optimal strategy about the problem. In this case, you know that we can calculate the sums by maintaining a running sum. So we just do that. And then you also know that as soon as it becomes greater than a target, we need to break out. And then you know the next thing, that when it becomes greater than the target, rather, you can simply update I. So this is what is called a greedy approach, where you somehow know that just doing this will fix it, right? There's no real technique to be applied, and these problems are somewhat tricky, but you get the hang of these problems as well. If you search for greedy problems online, you get the hang of these by solving a few practice exercises. Okay, so that's our first interview problem, and we've solved it in about 45 minutes. And this is approximately how long you will have for an interview. A typical 45-minute to 1 hour interview will have about a couple of minutes of introduction, maybe a few minutes just you talking about a project and the interviewer asking you questions. But then the next 30 to 40 minutes will be dedicated towards solving a problem. And this is what roughly the process will look like. Let's do one more example. Let's pick another interview question and let's see if we can solve this one. So this is slightly different. So this gives us one more variation to study. By the way, to run these, you simply click the run button and select run on Binder. Okay, so this is an interview question that was asked during a coding interview at Google. And the question is given two strings A and B. Find the minimum number of steps required to convert A into B. So what you can do is you can perform operations, and each operation is counted as one step. And the operations you can perform on a word are these. You can either insert a character into the word, or you can delete a character from the word. So for instance, here you can see that we are trying to convert intention into execution. So either you can insert a character, for example, you could insert C here, or you can delete a character. For example, you can delete I here, or you can replace a character. That is, you can take N and replace it with E. You can take T and replace it with X, and E does not need to be replaced. And here we've inserted C, and then here we've substituted N for U, right? So we've taken the word intention, and by performing a few changes character by character, by either inserting, deleting, or replacing a character, we have converted it into the string execution. So the number of steps required here is 1, 2, 3, 4, 5. Now here's a challenge for you. Try and work this out on paper and prove that this is the best solution. So because we need to find the minimum number of steps required to convert A to B. Okay. So that's the problem. And this is a moderately hard problem, and variations of this show up as well. So let's start applying the method. Now, when you hear the problem, a solution may not strike you up front. That's perfectly all right. Don't panic. Sometimes when you're not able to immediately come up with a solution or identify how to solve this problem, you enter a sort of panic and then you're unable to think. Don't do that. Remember, have faith in the method, and we will apply the method and come up with a solution step by step. So the first thing is to state the problem in your own words. So given two strings, we need to perform operations, a series of operations on the first string. So the operations could be deletion of a character, substitution of a character with another character, or insertion of a character. And through these operations, we need to convert it into a second string. Okay, we have understood the problem. If the interviewer had not given an example, either you can state the example or you can just ask for an example, whatever works for you. So we've stated the problem. Now, what are the inputs to the problem? So the inputs are two strings. So the inputs are strings like intention and execution. So let's see, maybe let's call them str1. This is intention. str2. This is execution. Now, one thing you have to be careful about here is you do not want to capitalize, because sometimes what might happen is this I may match up with an I here in the proper solution, but Python obviously treats small and capital letters differently. Python doesn't know that the I which is lowercase and the I which is uppercase is the same. So you will not be able to compare them. So just to keep things simple, either make everything uppercase or make everything lowercase. But yeah, this is what the input looks like. And the output is going to be a single number. So the output is simply going to be the edit distance. So let's just call it output 1, and it is going to be the number 5. And here is something that you can verify. So that's the input, that's the output. And function signature. So of course this term edit distance is how this problem is described, but here there is no edit, there's no concept of edit distance that's mentioned. So you can give a function name that makes sense for this problem. So find the minimum number of steps required to convert A to B. Okay, so let's just call it min steps for now. So the function definition would be min steps, and this would take an str1 and this would take an str2, and it would return an output. For now we'll just put in pass here. All right, so now we have already clarified the problem. If you had any questions, this would have been a good time to ask the interviewer and make sure that you have a clear understanding. Now you have stated the input, output, and function signature. The problem has been communicated back and forth properly. The first step is done. The next step is to list out some test cases, right? Once again, a very good quality listing out some test cases. So you can say that now I'm just going to list out a few cases that I want my function to cover, so that they will help me, it will help me while writing the code. Now one is the general case, which is listed above. So this would be intention, execution, and we can take a few more examples like this. Now one example could be where no change is required. So you are given the same strings. One case could be that all the characters need to be changed. So these are the two extreme cases. One is no change is required, and second is all characters need to be changed, maybe added, removed, deleted, lots of such things. Then you can check both strings of equal length. So in this case they are in fact of equal length. Unequal length, you can check both strings of unequal length. One of the strings is empty. Your function should be able to handle that too. Then you may check things like it will, if something only requires deletion, if something only requires addition, or if something only requires swapping, right? Such things. I guess this is pretty good at this point. So now we can probably move forward. So we have stated some test cases. Now you don't need to create all the test cases right now in an interview. It can take a bit of time. So let's just move ahead, and the next step is to come up with the simplest solution to the problem, which is also called the brute force solution. So now we have a lot more information about the problem, and in this meantime probably it has sunk into you and you may have been able to think of a brute force solution. But if not, don't worry, there is a simple trick I'll tell you which you can apply whenever you are stuck and you can't think of a brute force solution. So you're looking at it, intention, execution. What am I going to do? Am I going to start from the left and right? How do I check which one is, how do I know if this is supposed to be inserted or executed or replaced or substituted or deleted? So the simple trick is, whenever you're in doubt, think about recursion. See if there is a way to solve this problem recursively. And what do you mean by solving a problem recursively? Can you reduce the overall problem to a combination of one or more sub problems? So if you take a portion of the input, and can you solve the same problem on the portion of the input and then use that to solve the overall problem? Okay, so let's see if there is a recursive solution possible here. So here I have the same thing, intention and execution. Now with recursive solutions, normally you either start by looking at the first character or the last character. So let's look at the first character of each string, right? So we're given these two strings and we need to find the number of operations to change this string into this string. Let's look at the first character. Now suppose the first characters were in fact equal. Suppose this was not intention, but this was intention and this was execution. So now we compare the first characters and we know that the first characters are equal. Okay, so if the first characters are equal, then obviously neither of them needs to be deleted or removed, or obviously this character does not need to be deleted or removed or switched. It's already matching. So what we can do is we can just ignore the first characters and we can simply look at the remaining string. Okay. So intention and execution, because the first characters are already equal. Let's write that down so that we don't forget it. And this is the recursive solution. Now this is where you can take a moment to work this out on pen and paper, and that's perfectly all right. What helps is to just keep talking about what you're doing. But for recursion, now first thing we know is if the first character is equal, then ignore from both. So you just ignore the first character of both strings and simply recursively solve the problem for the sub list or the substring without the first characters in each of the strings, right? So you exclude E and exclude E from this and solve the problem for these two. Perfect. Now suppose the first character isn't equal. So that's another case now, right? So that is the case where you have intention and execution. So if the first character is not equal, then either the first character has to be deleted or the first character has to be swapped. So you may have to swap I with E, or the first character, or maybe something needs to be added before the first character. Okay. Now let's see one by one. So if the first character is not equal, either it has to be deleted or swapped, or a character inserted before it. There are only three possibilities, right? Of course, it's possible that we may do some other things, insert characters after it and so on, but at that position, after applying an operation, either the first character will get deleted or the first character will get swapped and will be changed to E, or the first character will now change to something else and the original first character will become the second character. Okay. Now let's look at each case. The first case is if it is deleted. Now the beauty of recursion is that we don't need to guess which solution it is. We can try all three recursively and then simply pick the best one. So suppose we choose to delete the first character. So suppose we say that we are deleting the first character. Now what that means is we've performed one operation and we've deleted the first character. So now what we are left with is this. So now what we end up is the string has remained the same, only the first string has changed where we have lost the first character. Now what we end up with is with a sub problem where we need to find the minimum number of steps to change intention, NTENTION, into execution. Okay. So in this case, if it has to be deleted, then recursively solve after ignoring first character of str1. Okay. That's one possibility. And you get the recursive solution and you simply add 1 to it. That tells you the solution if you delete the first character. The next option is that we change the first character I to E. Now if we change the first character I to E, so one operation has been performed, and then now these two have become equal. Now that these two have become equal, we can move this forward and we can move this forward. So now we can simply recursively solve the problem for intention and execution, find the minimum edit distance between the two, and simply add 1 to it to get the number of steps required to change intention to execution by swapping the first character, right, from I to E. So in this case, you recursively solve after ignoring the first character of each, right? So it is 1 plus, in both cases it is 1 plus the recursive solution after ignoring the first character of each, because the one operation is something that has been performed. Okay, now the final case. The final case is you have intention and execution. Now we decide that we are going to shift the string forward and we are going to introduce an E here. So we are going to introduce E here. So now what happens is the E is matching the E. Now I has gone on to the first position, I has gone on to the next position here. So effectively what has happened is that we need to recursively solve the problem for the original string intention and the second string with the first character removed, because we have inserted something before the first character in the first string, so that is going to match with the first character of the second string, and hence we simply need to recursively solve the problem for these two. So in this case what we are doing is the solution is 1 plus recursively solve after ignoring the first character of str2. Okay, sounds good. Looks like we've done that. Now what's the end solution going to look like, the end case? Remember, in recursion this is all well and good, but at some point we are going to hit some kind of an end. So let's see if we can define such an end scenario. So maybe let's say we have been performing recursion and then we ended up at a situation like this where there is nothing left in the second string, but you still have some characters left in the first string, right? So you're at this position now, and here this is gone, there's nothing left in the second string. So in this case, to change recursive to change TION into the empty string, all we need to do is delete all four. So if you have a few characters, if the second string becomes empty, then you simply find the number of remaining characters in the first string and delete them. So that is the number of operations, 4. The other possibility is that the second string still has some characters, but you've run out of characters on the first string. So if you've run out of characters on the first string, but the second string still has some characters, then in that case, what you need to do obviously is you have the empty string and you need to take this, convert this empty string into TION. That is a recursive problem we are solving. So you can do by adding TION. Great. So you add TION, and that is again going to be 4 steps, which is the number of characters remaining in the second string. Okay. So these are the two end cases. Now, of course, if both of them are empty, then the answer is 0. But if either of them is empty, the answer is the number of remaining elements in the other one. So let's write the solution. Now we figured out the solution. It took some time, but again, this is not a very straightforward problem. So there are a few cases to figure out. And while you are doing this, while you're identifying each case, either you can say it out loud to the instructor or you can write it as a comment, whatever you feel more convenient with, because the interviewer cannot see the work that you're doing on paper. So it's very important for you to be able to convey it. And that is why all this while in this course, we have been saying that you need to express the solution in simple words, because you need to tell the other person that you know the solution and they should be able to understand what you're saying without looking at your work, without looking at the images that you've drawn. And a great way to do it is either by writing or by speaking. Let's define it then. Def, what's it called? Min steps. And min steps is, it takes str1 and str2. Great. Now we are doing recursion, and in recursion, what we're tracking is which character we are currently at. So we could be at the 0th character or the first character or the second character in string 1. And we could be at the 0th character, first character, second character in string 2, right? So the starting point of this window determines the sub string that we are solving the problem for. So ideally, when we want to solve this problem for these two substrings, we can simply pass those substrings, but creating sub lists or substrings has a cost, because you have to copy those characters out and then allocate some memory and put them into a new place. So an easier way is to simply keep a pointer. So we will keep 2 pointers, I1 and I2. And these will signify that we should be skipping, while computing min steps, we should be skipping the first I1 characters, or we should be starting from the I1th index and we should be starting from the I2th index for str2. Okay. So in your window, if the I1th index, if the starting index is equal to the length of string 1, so this is the end case. And remember, the end case while coding is always written first. So if this is equal to length of str1, then we have seen here that we need to perform these many additions. So we simply return, in this case, str len of str2 minus I2, right? And you can verify that this is the number of additions required. Elif, on the other hand, I2 is equal to len of str2. So which means that you have exhausted the second string, but the first string still has some values left. So in this case, you need to delete the remaining values in the first string. So you just type len of str1 minus I1. Great. So these we have now solved the trivial cases. Now let's see elif str1 of I1 and str2 of I2, which means the first characters of each substring that we are working with, right? Remember, we are just using arrays as we're just using indices as a optimization. What we really want to work with is substring. So the first character of each substring, str1 of I1 and str2 of I2 is equal. Now, if the first character is equal, E and I are equal, then we simply ignore both and solve the problem for the remaining string. So we simply say return min steps, and we pass in str1, we pass in str2, and then we simply pass in I1 plus 1 here, and we pass in I2 plus 1 here. So what this is saying is that now we want to recursively solve the problem for a substring starting at I1 plus 1. So we have ignored the first string of the current substring, and similarly we have ignored the first character of the current substring of the second string. Okay, so we ignore the first characters and that's it. And there are no steps required here, no operations required here right now, because the first characters are equal. Now finally, this is the final case, else. Here we want to return 1. So we have to perform one operation. Either it is an insertion, deletion, or swap. And what we can do is we can recursively check the cost or the number of minimum steps required for each case of insertion, deletion, and swapping, and simply pick the minimum one. And if to it we add 1, then we get the total minimum number of steps we need to perform for the entire list, right? So again, recursion is very useful because you can simply assume that you have the function which solves the problem, and you simply need to take the result of the subproblem and combine them. So we take the minimum of, the first option is if the first character of str1 has to be deleted. So which is, let's say we choose to delete I. If we choose to delete I, then that means we have to solve the problem for these two. So we say 1 plus recursively solve the problem after ignoring the first character of str1. So we solve min steps for str1, str2. Now since we've deleted the first character of str1, we can skip ahead into the next, because we are solving the problem now starting from the next index, and I2 remains the same, right? So remember, here we have not affected I2. So we need to solve this problem recursively. So this was the case of deletion. Next, we have the option where you have swapped the first character. So we have taken E and we have converted we have taken I, converted it into an E. If we did that, so then we can say that, okay, now these two characters are matching. So now we can simply recursively solve the problem for the next character onwards after ignoring the current character. So this becomes str1 plus str2 plus I1 plus 1 plus I2 plus 1. Great. So this is swap or replace. And you might notice that this turns out to be the same recursive call as this, except that we will add 1 to it because we have done the swap. And finally, if you are adding, so if you're inserting, so finally, if you're inserting here something, so if you are inserting E here, let's say, so in this case, what we'll do is now we'll recursively solve the problem for intention and execution without the E in front. So we skip the first character of the second string. So we have min steps str1, str2, I1, and I2 plus 1. So this is rather nice and symmetric. And that's it. So this should be it. Let's run this. Okay, there is a syntax error here. That's perfectly fine. There needs to be a comma here. That's fine too. I make a lot of syntax errors all the time, and of course, off by one errors. I'm sure there are a few. But yeah, this is the minimum number of steps, and this is our recursive function. Not too bad. 2, 4, 6, around 8 lines of code. And let's test out some of the test cases here. I'm just going to copy the test cases out here below. And let's test a general case, which is intention and exception. So let's see min steps, intention and exception. It says 4. Okay, why does it say 4? Maybe let's test a more simpler case first, which is one of the strings being empty. Let's say we have intention and one of the strings is empty. So we will need to delete, let's just say int, and one of the strings is empty. This looks fine. We will need to delete all 3 of these. And that in some way tests out this case where, or sorry, tests out the second case where the second string is empty. Now we can test this case. In this case also the solution is 3. Great, looks fine. Let's test this case where str1 I1 and str2 I2 are equal. So if you have integer and let's say you have India, so in would be the same, so these would get skipped, and here is where the recursion would kick in. So t would have to be changed to d, and then you would have to add I and a. Okay, that looks fine too. And let's check intention and exception once again. I don't know what's wrong here. Let's see. So is it possible to do it with 4? I don't know. It's maybe possible to do it with just 4 changes. If you change I, you delete I, and then you delete n, and then you delete t. Delete I, substitute these 2. I don't think it is possible with just 4 changes. So there's probably an issue. I don't know what's wrong here. It's possible I may have made a mistake here. Let me try another. Saturday and Sunday. Okay. So Saturday, SATUR, needs to be changed to Sunday, SUN. Now S is the same. So ATUR needs to be changed to UN. So U remains the same. Now if we can, what we can do is we can probably delete A, delete T, and replace R with N. So this seems to be fine. All right, so we'll probably, unless I'm not seeing this, so you have intention and you have exception. Unless I'm not seeing something, it seems like we may have made a mistake. One thing we could do is we can simply print out the strings that we are checking. So let's see, str1 is I1 onwards and str2 is I2 onwards. So we're first checking intention and exception, then we check, let's also print the result here. Okay, so at this point I would probably look through the loop here and see if it is correct, coming properly. So you have intention and exception. First we delete I, then we delete N, then we delete N, then we delete T, then we delete, okay, then we compare E and E. So then we come back to N and exception, and so on. I think this might take some time to fix. We'll come back to intention and exception. But supposing we've solved the supposing we've written the recursive solution correctly, and I do have the recursive solution here. So let me just grab that and put that in here. Let's see what's different. Okay, probably the answer is 4 because I'm still getting 4. But supposing we have the recursive solution here. So we have min edit distance. This is the recursive solution. And now what you need to do is you need to find out the complexity of the recursive solution. So now to find the complexity of the recursive solution, what we can do is simply look at the recursive calls in the worst case. So how you start out is you start out with a string of length n1, let's say, and a string of length n2. You have one string of length n1 and one string of length n2. Then you call this min edit distance with i1 plus 1 and i2 plus 1. So str1 and str2, you call them with i1 plus 1 and i2 plus 1. So that's one possibility. Or you call 3 recursive calls. Now one recursive call is the good case where these two match up. So we want to look at the worst case where these two things don't match up. So in that case, you make 3 recursive calls, right? So you make 3 recursive calls, and in each recursive call, you are then going to reduce the problem size by 1. So you're either going to decrease I2, or you're either going to decrease the size of the first string, or you're going to decrease the size of the second string, or you're going to decrease the sizes of both strings, right? So just to keep things simple, let's assume that in all 3 we are decreasing the size of either one of the strings by 1. So we are decreasing the total problem size, which is n1 plus n2 by 1, right? So the number of levels of recursion is going to be the total length of each of the 2 strings. So let's maybe just draw that graph here as well. So let's take this. So here you have n1 comma n2. So let's assume these are the lengths of the 2 strings. Now n1 plus n2, what happens to it? Is that this n1 plus n2 calls 3 recursive functions. So there are 3 recursive functions. So let's just draw those 3 recursive functions. So we have those 3 recursive functions here. Let's take this too. And then in those 3 recursive functions, what we have is either you reduce the size of the first string, or you reduce the size of the second string, or you reduce the size of both strings. So either you end up with n1 minus 1 and n2, and let's reduce the size of that. Or we end up with n1 and n2 minus 1, or we end up with n1 minus 1 and n2 minus 1. Okay, so these are the 3 recursive calls that we're doing, and then each of these will once again make 3 more recursive calls. And so on. Now what is the overall depth of this recursive call? Now because we can see that each time the size of the problem reduces by 1. So if the size of the problem is n1 plus n2, in this case it reduces by 1, in this case it reduces by 1, and in this case it reduces by 2, but for simplification, let's say it reduces by 1 here. So the total size of the problem, the total number of levels in this tree, is going to be n1 plus n2. So you have 3 problems in the first layer. The second layer will have 3 square problems. The third layer will have 3 cube problems. So 3 times 3 times 3. And similarly, you can go ahead and you will find that at the last layer, you'll have 3 to the power n1 plus n2 minus 1 layers, right? And if you then add together all the layers, what you end up with is that total number of sub problems is 3 to the power n1 plus n2, right? So you have a total of 3 to the power n1 plus n2 sub problems that you end up creating. And because of that, you have the complexity 3 to the power of n1 plus n2 in this case. Okay, so that's the complexity. So here we have a recursive solution, and then we have the complexity of the recursive solution, which is exponential 3 to the power of n1 plus n2. Now at this point, it will make sense to add memoization. So whenever you see recursive solutions and you see repeated problems, for example, here itself, you can see a repeated problem. And then you can see that this problem will get repeated inside this problem and inside this problem too. So there are a lot of repetitions, and all we need to do is remove some of those repetitions. And to remove those repetitions, we can use memoization. So what happens in the memoized solution? It is exactly the same as the recursive solution, but before doing any computation, we check a memo, we check a dictionary if we already have the solution for the changing variables, which is I1 and I2. And if we have those solutions, what we need to do is just return them directly. If we do not have those solutions, we need to compute the solutions, put them in the memo, and then return the value from the memo. So let's write the memoized version. So we have min edit distance with str1 and str2, and this we are calling memo. Okay, this we are calling memo. So now we have a memo. The memo is going to be a dictionary, and the dictionary is empty. And then we define a function recurse. So in memoization, normally you have to write a recursive helper function. Now you can either write this outside or inside. I like writing this inside because, well, it will have access to str2 and they do not need to be passed in. So here we have I1 and I2. And first thing we do is we create a key. So the key is I1, I2. Now if key in memo, which means if we have already computed the solution, then we simply return memo of key. If not, then we have all the other cases. So now we have elif. Now we can check if I1 equals len of str1. In that case, don't return, set the memo of key to len of str2 minus I2. Elif I2 equals len of str2. Then we return memo of key is len of str1 minus I1. Elif, okay, in this case, then we check if the first elements are equal. So we have the exact same logic. You can see the same cases coming up here. So if you have str1 of I1 equals str2 of I2, in this case, we have memo of key equals, we simply ignore the first character. So we increment I1 and I2. So exactly what we have done here. So we simply call recurse this time with I1 plus 1 and I2 plus 1, right? So we always call the recursive function, but inside the recursive function, if it has already been computed, it will return from the memo. And finally, if we have, and this is the final case, which is where they are not equal. So here memo of key becomes 1 plus min of, let's see here. So we have recurse. So the insertion cases, we will ignore the first element. Sorry, the deletion cases, we will ignore the first element of the current range from the first string. So we call recurse with I1 plus 1 and I2. Otherwise, we call recurse with I1 plus 1 and I1 plus I2 plus 1. This is the case where we swap the first element of the first string. So we can just recursively check after ignoring the first element of each. And then we have recurse with I1 comma I2 plus 1. I2 plus 1. And there we go. And that's it. So now we have stored it in the memo, and then we simply return memo of key at the very end. And finally, we call recurse 0, 0, and that is our solution. Okay. And there is a syntax error. You can fix these syntax errors. They're easy to fix. And I've just realized that the solution in this case might actually be 4, because what we can do is we can change n to p. So that's one step. We can replace int with exc. So we replace int with exc. That's 3 changes. We don't change e, and we replace n with p. The solution is 4. So our solution was correct. There was no issue there. In fact, this is not the best solution. This is a suboptimal solution. So this output should be 4. And that's okay. This is something that happens all the time, where you miss something and you just assume that you just say that you're going to come back to it at the end, and then you move forward assuming that that code was right, and then you realize that either you were correct or what your mistake was. It's probably going to happen in one of 5 interviews anyway. Okay, so now we've written a memoized solution. Great. And we can start checking the memoized solution now. So minimum edit distance memo. So let's call min edit distance memo, and we get back the value 4. Looks fine. Let's try Saturday and Sunday as we have. So that's 3. So what you will do is you will leave a as it is, change atur to un by removing at and changing r to n. That seems fine. Let's test out some cases like this. Okay, this is 3, 6, 8 characters. So that seems right. We simply delete all the characters. Let's check out this. Here also 8 characters. We have to add 8 characters. Let's say we have ABC and XYZ. So this should be 3. If it is XYZK, then maybe that will be 4. What if it's XYZA? In this case also it's 4. So this seems to be working fine. We have now taken the recursive solution, identified the inefficiency, calculated the complexity, which was exponential, identified the inefficiency and which was repeated subproblems, and then fixed the inefficiency by calling min edit by using memoization. And now how do you compute the time complexity of memoization? Well, the argument is if you only need to compute the solution for a key once, and the computation apart from the recursive calls simply involves some comparison and a fixed number of comparison and an addition. So the time required to compute, assuming you have the recursive solutions, is constant. So that means if you simply count the number of memoizations that can possibly occur, that gives you an upper bound on the total number of operations. It will be some multiple of that, some constant multiple. So I1 can take the value 0 to n1, where n1 is the length of string 1, and I2 can take the value 0 to n2, where n2 is the length of string 2. So memo, the keys in memo can be I1, I2. So you have n1 values for I1, n2 values for I2. So that makes it n1 times n2. That's the number of keys, and that because there's a constant amount of time, additional time required to compute the solution for a key, that is also the complexity. So the complexity is order n1 plus n2. So we've gone from 3 to the power of n1 plus n2, which grows very quickly. Even for 3 to the power of 10 is pretty high. We can check it out here. 3 to the power of 10 is something like 59,000. 3 to the power of 100. So if you have n1 plus n2, then that's e to the 47. That's going to be a lot of operations. On the other hand, with memoization, it is only going to take, let's say the 100 is split as two strings of length 50 and 50, only going to take 2500 operations. So where it was taking 10 to the 47 operations, now it takes only 2500 operations, which is pretty small. So you can still work with lists of size up to 10,000 or 100,000 very easily using the Memoize solution. So that covers this problem. And keep talking through your solution even as you're stuck, even as you're confused, just as I was. It's helpful to just keep spend maybe 2 or 3 minutes trying to solve the issue. And if you're not able to solve the issue, just say that this is something I'll fix later, and then move on, assuming that you've fixed it, and then keep talking and keep working on the solution. And at some point later, it's possible that the solution might strike you. Okay. Now at this point, you may be asked sometimes to implement a dynamic programming or an iterative solution. Like when you talk to the interviewer and you're telling them that this is how I'm thinking, I'll do a recursive solution first, and I can see that maybe there are going to be some sub problems there. Then I'm going to apply dynamic programming. So you can just check with them, and in most cases they will accept a memoization solution, because the dynamic programming solutions can take a little bit of time to solve, to implement, and there are always off by one errors, and it's also difficult to explain the solution. So you can most cases get away with memoization. But if they do ask you to do it iteratively with dynamic programming, then you'll have to go ahead and implement the dynamic programming solution. So once again, take a couple of minutes now and work it out on a piece of paper, and then go back to them. Now for dynamic programming, remember you have to create a table essentially. So what the table will look like in this case is, let's see if we can simulate a table. So what the table will look like is, let's create a new sheet. And in this sheet, let us put the two words, which is intention okay, and let's put the word exception as well. Move this down too, and let's also put in the indices. Ultimately, this is what a dynamic programming problem looks like. You are ultimately going to create a table here. And how we'll start filling the table is the ijth element. So let's say this element, INTE. So this element represents the edit distance, or the number of operations required to convert INTE into EXCE. And how do you check what the solution is? Now you know that E and E are equal, so the final elements are equal. So what that means is, we look at this value, then this value should tell us what is the minimum edit distance between EXE and EXC. Now since we can simply add E to each string and get this solution, that means this solution is equal, this value is equal to this value. All right. So in the case where the corresponding elements are equal, we simply copy over the value diagonally left, top left value onto the current cell. The other option is if they are not equal. So let's say if we are here, where here you have N and here you have P. Now there are three possibilities. You want to find the minimum edit distance between INTEN and EXCEP. Now N is not equal to P, and this is the original string. So either we delete N. Now if we delete N, then we need to find the solution for INTE and EXCEP. So if we delete N, then this value will become 1 plus this value. That's one possibility. Or another possibility is that we swap N. So we swap N for P. So now you get this becomes P and this becomes P. So this value will become 1 plus this value, because now we can ignore the P and simply get this previous solution for EXCE and INTE. So this value becomes 1 plus this value. Or the final option is that you can insert something just before N. So if you insert something just before N, which is going to be P. So if you insert P just before N, sorry, you insert P just after N, not before. If you insert P just after N, then you have P after it already. So you can just look at this value, and this value is going to be 1 more than this value in the case that you insert something, insert P after N, right? So there are 3 ways to come to this value, either by deleting N, or by inserting P, or by changing N to P. And what you can do is you can take the minimum of 3 values, these 3 values, and add 1 to obtain this value. So that's the logic, roughly speaking. And you start from the left. So you see, okay, E and I, they are unequal. So you need one operation to change them, and there's nothing else to consider. So that's done. Then E and N, they are unequal. Now you need, what you can do is you can either delete N. If you delete N, then you simply need to check E and I. And you know that the solution for E and I is 1. So this would be 2. Another option is that you could possibly insert something. But if you insert something, the length of IN is going to increase. So that's going to cause a problem. So you can't insert anything. Another option is you change N with E. But if you change N with E, then you will no longer be able to. If you change N with E, then you will no longer be able to use this solution, right? Because now you will have to match I with the empty list. So that's going to be 1 as well. So overall you end up with 2. And this is how you start filling the list. So you start filling up from left to right and left to right and keep going top to bottom. And as you fill out this list, finally you will fill out this final value, exception and intention, and that will be your solution. So that's the dynamic programming solution, and you can see that it's getting tricky to convey the entire solution because there are so many cases involved here. So typically you will not find dynamic programming solutions requested in interviews, and it will help you to just stick to the memoization solutions. All right. So with that, we have covered 2 common interview questions, and you can keep going. So the idea here is to just apply the method. Remember the method, the problem solving template that we've covered. State the problem, identify input and output formats, write a function signature, come up with some example inputs and outputs, or at least the scenarios, come up with a correct solution, state it in plain English, implement the solution, test it using example inputs, and fix bugs if you face any. Then analyze the algorithm's complexity and identify inefficiencies, and finally apply the right technique to overcome the inefficiency. And you repeat the process, going back and stating the solution, implementing, analyzing, and repeating. Now in some cases you do not need to implement the brute force solution if you don't have the time, but when you're working with recursive solutions, it always helps to implement brute force first before you do memoization or dynamic programming. And some tips: ask questions, as many questions as you can, as many as you need to clarify the problem. Show an example, follow the method, don't panic. If you get stuck at a certain point, give it a couple of minutes. Sometimes you can even ask the interviewer and they may be able to tell you that maybe what your error is, or maybe you're not stuck at all, what you're simply assuming something incorrectly. But beyond a few minutes, what you want to say is that I'll fix this later, assuming this is correct, let's move on, and then talk about complexity and optimization and such and such. Okay. Very important is to state the brute force solution to the interviewer, and if you are unable to figure out a more optimal solution, then the best thing you can do is to offer to implement the brute force solution, so that you can at least demonstrate that you are able to write code. And it's all right, in a lot of cases you will not be able to figure out the optimal solution, and in some cases there may not be an optimal way. So there are certain problems where there is just one way, and that is the hard way or the brute force way. And this is typically very true with a family of problems called backtracking, something we've not really covered in a lot of detail, but it is also another form of recursion. So what do you do next? So the next step for you is to review this lecture video and solve these problems yourself, or take more problems. Ideally, what you want to do is you want to take all the 5 different techniques that we've covered, and let's quickly review what those 5 techniques were. The first one was binary search. So we looked at linear search and binary search, which is a form of divide and conquer. And along with that, we also understood the complexity and big O notation. And then you had some homework on linked list and Python classes. But binary search is something that comes up often. And the hint to detect binary search is simply to look for order. Whenever you see something being mentioned as sorted, now that is an indication for you that this may be binary search. Sometimes what you may have to do is you may have to get things into a sorted form, maybe by replacing elements by sum of values till that element or so on. And once you get things into a sorted form, maybe then you can do binary search. That's one way to go about it. And once again, just do 5 to 10 problems on binary search and you will be able to identify pretty much any binary search question in an interview. Then the next topic that we looked at was binary search trees, traversals. And here is something that is generally asked very directly. So you will be given a question like binary search tree, do something with a binary search tree, and you can answer that question directly. We've covered a lot of different things here, so do check out lesson 2 for all the different things you can do with binary search trees, traversals, balancing, and most of these are recursive solutions, so it's also a good exercise on recursion. And we've also looked at balanced binary trees and how can we optimize them further. Then you had an assignment on hash tables. So hashing is again a common question that is often asked. So we built hash tables from scratch in Python, and we also handled collisions using a technique called linear probing. And so this is something you can check out in assignment 2. So you may get asked just to implement a hash table in Python or implement collision resolution in a hash table, in which case you can use linear probing. Then you have the sorting algorithms, where we looked at bubble sort and insertion sort, merge sort using divide and conquer, and quick sort, where we had a quadratic worst case complexity but a logarithmic average complexity. And that's a good thing, because merge sort, although it is logarithmic in the worst case, it still takes up a lot of space, and space allocation is slow, and you may also not have the memory. So that's why we sometimes prefer quick sort over merge sort when we are constrained for space. Then assignment 3 is pretty interesting, where you will implement an optimal algorithm for polynomial multiplication using divide and conquer. So do check out assignment 3 as well. Then we looked at dynamic programming, we looked at recursion, memoization, subsequence and AppSack problems. And then we finally also didn't cover backtracking and pruning, but there are some questions there in the lesson notebook which you can try out, which use backtracking and pruning as well. Then we looked at graph algorithms the last time, which was graphs and adjacency lists and adjacency matrices. We looked at the depth first and breadth first search and how to implement them. And we also looked at shortest paths and directed and weighted graphs. This is a very important topic, breadth first and depth first search. You will get many questions related to these. So do solve maybe 5 questions on each of these topics, and you should be good with most graph problems asked in interviews. Now this project for you, the course project, if you haven't seen it already, is to pick a coding problem. So you can pick a coding problem from an online source like LeetCode, HackerRank, Geeks for Geeks, etc. And then use the problem solving template that we've shared with you. This problem solving template as a starting point. So just give it a name and then write the problem statement and implement the solution step by step. So use the problem solving template to solve the problem using the method you've learned in the course. Then document your solution, add explanations wherever required, perform the complexity analysis. All of this you should add in the Jupyter notebook and then publish your notebook to your Jovian profile. And finally, you can submit the link to your Jovian notebook here. So submit the link to your Jovian notebook here. And you can check out the discussion where you can change, where you can post what you're working on. So do post your notebook as well. And finally, today we have looked at a couple of real interview questions from Amazon and Google and how to go about solving them. And we also addressed a few issues that we faced along the way. So that was a helpful exercise. And that's it. So now you can review the lecture video, execute the Jupyter notebooks, complete the assignments and attempt the optional questions so that the topics that we've covered, they get consolidated and you do not ever have to look at this lecture again, right? So practice is what really reinforces and consolidates your learning. Complete the assignments and attempt the optional questions to practice, and participate in forum discussions. Also very useful. When you participate in forum discussions, by answering questions, a lot of your own doubts get cleared. So do participate in forum discussions, and then join or start a study group if possible. Getting together with a group of 4 or 5 people is great. It really helps you focus and improve your understanding by discussion. So that's data structures and algorithms in Python. So with that, thank you very much for joining us on this journey as we learn data structures and algorithms in Python. A very useful topic to improve your coding skills, and also something that you will almost certainly encounter in one of your interviews, no matter which company you're applying to. So I hope this is helpful to you. Do let us know on the forum how this course helped you. If it did, you can let us know in the YouTube comments as well. If you have questions, if something was not clear, do post that too. And we'll make sure to come up with clearer explanations and clearer examples the next time. If you have any feedback for us, do post it in the comments or send us an email at support@jovian.ai. With that, I will take leave and I will see you in the forums. This is not the end of our journey with you. So do stay active on Jovian. There's a lot of great activity happening. Do check out the forums, the newsletter, and stay tuned for our next course. Thank you and goodbye.